The largest dinosaurs to ever walk the earth were living mountains of flesh and bone, towering so high and weighing so much that their very footsteps could shake the ground. To cross paths with one in the wrong moment would mean facing a death unlike any other in the natural world. A death not from claws or fangs alone, but from forces so overwhelming that the human body would be no more than a fragile shell against them. To be crushed beneath the colossal weight of a sauropod, swept aside by the swing of a massive tail, or torn apart by the sheer bite force of a predator like Spinosaurus or Tyrannosaurus, would be to experience nature's most brutal extremes. From colossal dinosaurs to the most massive snakes ever known, meeting one of these creatures up close would almost certainly spell doom. So, what would those final moments actually look like? Before we start, let us know in the comments below where in the world you're watching from and what time it is there. Now prepare for a journey back to the prehistoric era. Titanoboa was a snake unlike anything that exists today. It was not just big, it was a creature so enormous that it has become legendary in paleontology, the science that studies ancient life. This snake belonged to the boid family, which includes all modern boas and anacondas. Titanoboa lived during the middle and late part of the Paleocene epoch, a time that stretched roughly from 60 million to 58 million years ago. That was only a short while in geological terms, after the cataclysm that wiped out the dinosaurs at the end of the Cretaceous period. When the dinosaurs were gone, giant reptiles like Titanoboa rose to dominate the tropical world. The story of Titanoboa begins in the early years of the 2000s. In the coal mines of Cerrejón, located in La Guajira, a dry and rugged region in the northeastern corner of Colombia, something extraordinary was hidden under layers of earth and rock. A group of researchers from the Smithsonian Tropical Research Institute, working together with students from the University of Florida, uncovered fossils that would change the way scientists think about prehistoric snakes. In total, they recovered 186 fossil pieces belonging to Titanoboa. These remains included mostly thoracic vertebrae and ribs, but later expeditions also managed to uncover parts of the skull and even some teeth. The fossils were first carefully studied, and in the year 2009 the animal was formally named Titanoboa kerajonensis, in honour of the Cerrejón mines where it was discovered. When Titanoboa was first described, it immediately claimed the title of the largest snake ever known to science. Estimates showed that this snake could reach a length of up to 12 8/10 meters, which is about 42 feet, and some individuals may have stretched to as much as 14 3/10 meters, about 47 feet. Its body mass was also astonishing, with weight ranging from around 730 kilograms to over 1,100 kilograms, which is between 1,600 pounds and 2,500 pounds. To put that into perspective, a fully grown Titanoboa was heavier than a small car and longer than a city bus. Before the discovery of Titanoboa, the record for the largest snake belonged to another prehistoric serpent called Gigantophis garstini, which lived during the Eocene epoch in what is now Egypt. But Titanoboa surpassed Gigantophis by several meters, leaving no doubt that it was a true giant of the Paleocene world. The first fossils of Titanoboa were uncovered in the year 2002 during a scientific expedition organised by the Smithsonian Tropical Research Institute and the University of Florida. Among the students participating were Jonathan Bloch and Carlos Jaramillo, who played key roles in the discovery. At first, when the fossils were dug out of the blackened coal beds, they were mistaken for the bones of crocodiles. This was not surprising, since the Cerrejón Formation also contained the remains of massive crocodilian species as well as giant turtles. But closer examination revealed that many of these bones belonged to something far stranger, a snake of truly enormous size. Over the next 2 years, from 2002 to 2004, more fossils were uncovered, eventually adding up to about 186 pieces from at least 30 different individual snakes. These fossils were then transported to the Florida Museum of Natural History, where a team of international scientists from Canada, the United States and Panama studied them in detail. In 2009, Jason J. Head of the University of Toronto led the research group that officially described the new species. They named it Titanoboa kerajonensis. The genus name Titanoboa combines the Greek word titan, meaning giant or godlike in size, with boa, the type genus for the family Boidae. The species name Serajonenses refers to the Serajon mines. The holotype specimen, the official fossil that defines the species, was a single dorsal vertebra. By studying its proportions, the team was able to calculate the approximate size of the animal. Another major breakthrough came in the year 2011, when a new expedition to Serajon uncovered even more material. This time, researchers found 3 partial skulls of Titanoboa. Fossilized snake skulls are extremely rare because the bones are fragile and tend to break apart, so this was an extraordinary find. These skull pieces, though still not fully described in scientific papers, gave paleontologists new insights into how Titanoboa looked and lived. In the year 2012, the British Broadcasting Corporation aired a documentary called Titanoboa, Monster Snake, which brought the creature into popular imagination. A travelling exhibit of the same name toured museums from the year 2013 until the year 2018, allowing the public to marvel at reconstructions of the beast. By comparing the vertebrae of Titanoboa with those of modern boas, scientists were able to refine their size estimates. They discovered that Titanoboa's body was built from very robust wide vertebrae with a distinctive pentagonal shape when viewed from the front, a feature common in the boid family. Modern boas and pythons achieve greater size not by having more bones in their spine, but by enlarging the vertebrae themselves. This means paleontologists can make reliable length estimates even from a single vertebra. The vertebrae studied from Titanoboa came from a position about 60 to 65% down the snake's body, which made the calculations more accurate. The results showed that Titanoboa reached an average length of about 12 8/10 meters, plus or minus about 2 meters, with some specimens possibly longer. When compared with modern snakes such as the green anaconda and the reticulated python, Titanoboa far exceeded them both. Even the largest anaconda, which may reach around 6 to 7 meters, would have been only about half the length of Titanoboa. Weight estimates placed Titanoboa between about 650 kilograms and more than 1,800 kilograms, depending on which comparison method was used. The most reasonable estimate suggested a weight of about 1,100 kilograms, or around 2,500 pounds. Later discoveries of skull material allowed scientists to refine the estimates further. By applying the proportions seen in anacondas, where the length of the skull is compared to the total body length, researchers calculated that Titanoboa, with a skull about 40 centimeters long, could have reached a maximum body length of around 14 3/10 meters. That is nearly 50 feet, longer than most school buses. In 2016, another team used new mathematical equations to estimate that a Titanoboa of 12 8/10 meters would weigh about 730 kilograms, a figure closer to the lower end of the earlier estimates. Titanoboa was not just remarkable for its size, its lifestyle was also fascinating. Fossil evidence suggests that it was a semi-aquatic predator, much like today's green anaconda. The Serajon region during the Paleocene was a hot, humid, swampy jungle, with wide rivers and dense vegetation. At that time, global temperatures were higher than they are today, creating a tropical climate even closer to the equator. In this watery world, Titanoboa thrived. Its diet likely consisted mainly of large fish, which were abundant in the rivers. Unlike land-dwelling constrictors that prey on mammals or birds, Titanoboa seems to have specialized in hunting giant fish, making it the top predator of its ecosystem. The discovery of Titanoboa was more than just the unveiling of a giant snake. It also offered scientists a window into an ancient environment that had previously been poorly understood. Before Titanoboa's fossils were found, very few vertebrate fossils from the Paleocene tropical regions of South America had ever been studied. The Serajon Formation changed that, revealing not only snakes but also giant turtles, massive crocodiles, and the remains of early plants that would eventually give rise to the lush tropical rainforests we know today. Titanoboa also helped scientists understand the relationship between climate and animal size. Because snakes are ectothermic, meaning their body temperature depends on external heat sources, their maximum possible size is strongly influenced by the warmth of their environment. The fact that Titanoboa could grow so large suggests that the tropical climate of the Paleocene was much hotter than it is today, perhaps by as much as 5 to 10 degrees Celsius. This gives researchers important clues about how ecosystems respond to changes in global temperature. Although Titanoboa held the crown as the largest snake for many years, Paleontology is a field where new discoveries can always change the picture. In the year 2024, another giant snake was described, Vasuki indicus, a madtsoid from India. Vasuki may have reached an even longer body length than Titanoboa, though its vertebrae were somewhat smaller and more delicate. Still, Titanoboa remains unmatched in terms of its overall mass and bulk, making it one of the most imposing reptiles ever to have existed. Even with these later discoveries, Titanoboa's importance cannot be overstated. The fact that 8 different specimens of similar size were found suggests that such gigantic proportions were not rare accidents, but rather the normal size range of the species. This means Titanoboa was a true giant by nature, not just a one-time freak of growth. The fascination with Titanoboa has spread far beyond scientific journals. Popular media, documentaries, and exhibits have brought the snake to life in people's imaginations. It represents not only the awe-inspiring size of prehistoric animals, but also the mysteries of worlds long gone. Walking through a rainforest today, one might encounter snakes, crocodiles, and turtles, but nothing comes close to the overwhelming dominance of Titanoboa in its swampy domain. It was a predator so large that no other animal could rival it. Many of the remains of Titanoboa that scientists have uncovered are far from complete. In fact, most of what we have of this enormous snake are bones from its backbone, particularly from the middle section of its body, located before the cloaca, which is the common opening used by reptiles for reproduction and waste. These fossilized bones are mostly thoracic vertebrae, and they carry special features that make Titanoboa stand out, even though it shares many general similarities with other members of the boa family. Like modern boas, its vertebrae show a short projection called the Prisogappa physial process, which points backward. But in Titanoboa, these bones are thicker, stronger, and heavier than in any other boa, and they show a unique T-shaped ridge along the top known as the neural spine. This neural spine has an expanded rear margin and a thin, blade-like front edge, giving the vertebrae a look unlike those of other giant snakes. Small pits, called foramina, are present on the surface of these bones, but in Titanoboa, these openings are noticeably smaller than those in most other boid snakes. When it comes to the skull of Titanoboa, things are even more mysterious. For a long time, almost nothing was known, and it was not until the year 2013 that a short scientific abstract briefly described parts of the skull. From this description, it appears that Titanoboa had far more tooth positions than most of its relatives, both along the roof of its mouth, the palate, and along the edges of its jaws, the marginal tooth positions. Its quadrate bone, which connects the skull to the lower jaw, was tilted at a low angle, and the connections between several key bones, the palatine to the pterygoid and the pterygoid to the quadrate, were greatly reduced. These unusual features were not seen in other boas. Even the teeth themselves were distinctive. They were weakly anchored to the jaw, a condition called weak ankylosis, meaning they were not firmly fused but rather lightly attached. This would have made the teeth easier to lose and replace. Scientists have placed Titanoboa in the family known as Boidae, a family that includes the constrictor snakes. This family of snakes first appeared during the late Cretaceous period, more than 66 million years ago, in the lands that are today the Americas. They spread far and wide and are today divided into 6 subfamilies found across almost every continent. Titanoboa belongs to the subfamily Boinae, which is known from the shape of its vertebrae. All living members of this group today are found in the Americas, stretching from Mexico and the islands of the Antilles all the way down to Argentina. Interestingly, Titanoboa is the only member of this group that has gone extinct. Every other genus of boins still has living representatives today. The skull fragments that were finally studied confirmed Titanoboa's place in this subfamily. Its reduced palatine chonal opening, a feature of the palate, supports this placement. The abstract from the year 2013 even suggested that Titanoboa may have been closely related to snakes from faraway places such as Madagascar and islands of the Pacific Ocean. This would mean that there was once a link between boas of the Old World and those of the New World, and that the two groups may have separated from each other by the Paleocene period, which began about 66 million years ago. If so, Titanoboa would be one of the earliest members of its subfamily, a view later confirmed by a study in the year 2015. For years, researchers thought Titanoboa behaved much like today's green anaconda, mainly because of its gigantic size and the swampy, forested environment where it lived. The common belief was that it preyed on crocodile-like reptiles that lived alongside it. but when Jason Head and his colleagues examined the skull in the year 2013, they noticed something remarkable. Titanoboa's skull was better suited for eating fish. Its jawbones, palate and tooth count all pointed toward a diet based on aquatic prey. This meant Titanoboa may have been a piscivore, a fish eater, much like certain modern snakes that specialize in this lifestyle. Such an adaptation made sense because the region where Titanoboa lived, in what is now Colombia, was filled with huge river systems during the Paleocene. Fossils of large freshwater fish, including lungfish and ancient relatives of modern bony tongues, have been found there, giving further evidence that Titanoboa had plenty of fish to feed on. The land that Titanoboa called home was part of the Cherion Formation in northern South America. During the Paleocene, this region was a coastal plain covered in hot, humid tropical rainforest with large and winding rivers. These waters and forests supported an incredible range of life. Several types of crocodile-like reptiles known as Dinosaurs thrived there. They had survived the mass extinction that wiped out the non-avian dinosaurs and were not directly related to modern crocodiles. Among these Dinosaurs were three types that lived alongside Titanoboa. There was the long-snouted Acherontissuchus, the broad-headed but medium-sized Anthracosuchus, and the smaller Deinosuchus. Giant turtles also thrived in this environment. Some of them grew truly enormous, such as Pterogonomes and Carbonomes, which swam in the same wetlands as Titanoboa. The rainforest environment where Titanoboa lived looked in many ways like the tropical forests we know today. The same plant families dominated, such as ferns, palms, and flowering plants, like those in the ginger and arum families. But the diversity of these Paleocene forests was much lower than that of modern rainforests. Scientists think this reduced variety of species may have been caused by the massive extinction event that ended the Cretaceous period only a few million years earlier. It seems that the forests that grew back after the extinction had simpler ecosystems compared to today's, even if they were just as lush and green. In the year 2009, when Titanoboa was first formally described, Head and his colleagues suggested that the snake's enormous size was connected to the climate it lived in. Being a cold-blooded animal, or more precisely an ectotherm, Titanoboa depended heavily on the outside temperature to regulate its body heat. Warmer climates generally allow cold-blooded animals to grow larger because their metabolism works more efficiently in heat. Since Titanoboa was so massive, it hinted that the Paleocene tropics were even hotter than those today. By comparing the maximum size of modern anacondas to their habitats, Head and his team estimated that the average yearly temperature in Paleocene Colombia must have been at least 32 to 33 degrees Celsius, or around 90 to 91 degrees Fahrenheit. This agreed with earlier studies published in the year 2003, which had also suggested that the Paleocene was a greenhouse world with extreme heat and rainfall. However, not all scientists agreed. Some argued that this method of linking body size to climate was unreliable. J.M. Cale Snyderman, for example, tested the same idea on a giant monitor lizard from the Pleistocene epoch called Varanus priscus, sometimes called the Megalania. His calculations showed that if this method were correct, today's tropics should be able to support lizards far larger than those alive now, or that Varanus priscus should have been much smaller than its fossils suggest. This led him to argue that Titanoboa's great size may not have been caused by hotter temperatures at all, but instead by the lack of competition from large mammals, which was still scarce in the early Paleocene. Other researchers, such as Mark Denny, Brent Lockwood, and George Somero, also disagreed. They noted that while the method may work for smaller reptiles, it breaks down with truly giant animals. If Titanoboa lived in an environment as hot as suggested, they argued, its huge body would have overheated whenever it coiled up. They proposed instead that Titanoboa's lifestyle, posture, and perhaps its semi-aquatic habits played a more important role, and that the actual climate may have been 4 to 6 degrees Celsius cooler than Head's team estimated. Head and his colleagues did not leave these challenges unanswered. They responded the very same year, arguing that critics misunderstood their model. They explained that their method accounted for differences in body size and was based on the largest living snakes, making it suitable for Titanoboa. They also reminded others that large modern snakes are known to control their temperature by basking, moving in and out of shade or adjusting their posture. As for the comparison with Komodo dragons, they pointed out that these lizards are restricted to small islands, which naturally limit their growth, unlike mainland snakes such as anacondas or Titanoboa. Finally, they challenged the fossil size estimates of Varanus priscus used by Snyderman saying they were exaggerated. More reliable data suggested the lizard was between a little over 2 meters and about 4.5 meters long, not the extreme length sometimes reported. Deinosuchus was one of the most fearsome creatures to ever glide through the waters of prehistoric Earth. It belonged to a group of reptiles known as crocodilians, relatives of the modern crocodiles and alligators that lurk in rivers today. Scientists are still debating its exact place in crocodilian family history. Some believe it was a close relative of the alligator lineage, while others see it as part of a more ancient stem group, standing as a distant cousin rather than a direct ancestor. Regardless of these debates, one fact remains clear. Deinosuchus was a giant unlike anything alive today. It prowled the swamps, rivers, and coasts of the late Cretaceous period, a span of time that stretched from around 83 million years ago to 72 million years ago. The very first hints of this monstrous predator came to light in the United States during the middle of the 19th century. In the 1850s, fossil hunters working in the state of North Carolina stumbled upon enormous fragments of teeth. At the time, scientists did not realize what animal they belonged to. These discoveries would eventually prove to be the earliest signs of Deinosuchus, but in those days they were mistakenly assigned to a completely different animal. It was not until the year 1909 that the name Deinosuchus was officially given to the giant, a name born from the Greek words deinos, meaning terrible, and suchos, meaning crocodile. The terrible crocodile had finally been recognized. In the decades that followed, additional fossils began to surface. In the 1940s, more fragments of this colossal reptile were uncovered and studied. These bones were eventually assembled into a skull reconstruction at the American Museum of Natural History in New York. The model was striking and caught the imagination of the public, but it was also flawed. The scientists who built it did not yet know the true proportions of the animal's skull, and as a result the reconstruction greatly exaggerated its size and shape. Despite its errors, this model became the image that most people associated with Deinosuchus for many years. It stood as a symbol of a crocodile so massive it could rival dinosaurs in power. What made Deinosuchus so extraordinary was not only its size but also its mixture of familiar and alien features. In its overall shape, it looked very much like a modern crocodile or alligator. It had the same long armoured body, the same powerful jaws, and the same deadly tail designed for swimming. Yet, it towered above its living cousins. The largest adults grew to lengths of more than 10 meters, which is equal to around 35 feet from the tip of the snout to the end of the tail. To put this into perspective, that is roughly the length of a city bus. A modern saltwater crocodile, the largest living reptile, rarely exceeds 6 meters, making Deinosuchus nearly twice its size. Its jaws were lined with enormous teeth that were thick and blunt, perfect for crushing through bone and shell rather than for slicing. Along its back, a thick shield of rounded bony plates called osteoderms offered protection, giving it the look of a living tank. Studies suggest that Deinosuchus lived a surprisingly long life compared to its modern relatives. Where modern crocodiles may live for several decades, Deinosuchus might have survived for as long as 50 years. Its growth was steady, much like the crocodiles of today, but it kept on growing for far longer, adding size year after year until it reached monstrous proportions. Fossils of Deinosuchus have been discovered across a wide area of North America. They have turned up in at least 12 states in the United States, stretching from the East Coast all the way into the interior. Remains have been found in states such as Texas, Montana, and along the Atlantic seaboard. Pieces have also been unearthed in northern Mexico. During the late Cretaceous period, much of the continent was split in two by a vast body of water known as the Western Interior Seaway. Deinosuchus lived along the coasts of this seaway, thriving on both the eastern and western sides. In the western habitats, particularly near what is now Texas, Deinosuchus grew to its largest size, while in the east it was more numerous, though slightly smaller. Scientists still debate whether these differences in size and distribution mean that there were actually two separate species of Deinosuchus rather than one. As an apex predator, Deinosuchus ruled its watery domain. Its sheer power meant that few creatures could escape if it struck. Evidence suggests that it may have been capable of killing and eating even large dinosaurs that wandered too close to the water's edge. Its crushing teeth were strong enough to snap through the thick bones of prey. In addition to dinosaurs, it likely feasted on sea turtles, fish, and any other animal, that was unfortunate enough to cross its path. In this way, Deinosuchus filled the role of a super predator, much like lions and tigers do on land today. The early scientific history of Deinosuchus is filled with missteps and re-examinations. In the year 1858, a geologist named Ebenezer Emmons described 2 large fossil teeth found in Bladen County, North Carolina. At that time, he believed they belonged to a genus called Polyptychodon, which he thought was a kind of crocodilian reptile. He gave them the name Polyptychodon rugosus. Later on, scientists learned that Polyptychodon was not a crocodilian at all, but a marine reptile called a pliosaur. The thick, grooved teeth that Emmons studied were almost certainly the first scientifically described remains of Deinosuchus, though no one realised it then. In the year 1869, another paleontologist, Edward Drinker Cope, described a large tooth from nearby Sampson County, also in North Carolina. He called it Polydecty biturgidus. This too was almost certainly from Deinosuchus, though at the time the connection was not made. More substantial remains came to light in the early 20th century. In the year 1903 at Willow Creek in Montana, fossil hunters John Bell Hatcher and T.W. Stanton found several strange bony plates on the surface of the soil. At first, these were thought to belong to an armoured dinosaur called Euplocephalus. However, further excavation led by W. H. Utterback revealed more bones, including vertebrae and ribs. It soon became clear that these were not the remains of a dinosaur but of a gigantic crocodilian. Hatcher, upon learning this, lost interest in the fossils, as his focus was dinosaurs rather than crocodiles. After his death in 1904, the fossils were studied by his colleague W. J. Holland. Holland described the material and named it Deinosuchus hatcheri in 1909, honouring Hatcher with the species name. Later, in the year 1940, an expedition by the American Museum of Natural History uncovered more giant crocodilian fossils, this time in the rugged landscapes of Big Bend in Texas. These fossils were studied by Edwin H. Colbert and Roland T. Bird, who in 1954 gave them the name Phobosuchus riograndensis. Eventually, other scientists, including Donald Baird and Jack Horner, realized that these fossils also belonged to Deinosuchus, and the name Phobosuchus was abandoned. That name, created by Baron Franz Nopcsa in 1924, had been applied to many different crocodilian fossils that turned out not to be closely related. The scientific community gradually recognized Deinosuchus as the rightful name for these colossal reptiles. The American Museum of Natural History attempted to restore the skull of Deinosuchus using fragments of jaw and skull bones. The reconstruction was modelled after the modern Cuban crocodile, which seemed like a reasonable choice at the time. Colbert and Bird even stated that their reconstruction was conservative, because if they had used the long-snouted saltwater crocodile as a guide, the skull would have been even larger. Unfortunately, they did not know that Deinosuchus had a broad snout, and their model exaggerated the skull's size and width. Despite this mistake, the model became famous. It was the first time the public could see what a giant crocodile from the age of dinosaurs might have looked like. The plaster skull stirred imaginations and made Deinosuchus a prehistoric celebrity. Over the following decades, more fossils continued to appear. Many of them were only fragments, such as bits of bone and scattered osteoderms, but even these small pieces told important parts of the story. Paleontologist Chris Brochu once remarked that the osteoderms of Deinosuchus were so distinctive that even if they were found mixed in a jumble of other fossils, they could still easily be recognized. By the early 2000s, enough cranial bones had been found to allow scientists to build a far more accurate picture of the animal. In 2002, paleontologist David R. Schwimmer created a computer reconstruction that represented about 90% of the skull. This reconstruction gave the world its clearest view yet of the true proportions of the terrible crocodile. Even with these advances, knowledge of Deinosuchus is still incomplete. We know it was a giant crocodilian, armoured and deadly, able to live for half a century, and capable of preying upon the mightiest dinosaurs of its time. We know it haunted the waterways of North America, from the warm coastal plains of Texas to the swampy regions of the East Coast, and even into the lands of modern Mexico. We know it left behind teeth and bones that puzzled scientists for decades before the truth emerged. But much about its lifestyle, its exact diet, and whether the eastern and western populations truly represent different species remains a matter of study and debate. What cannot be denied, however, is that Deinosuchus was one of the greatest predators to ever live. In the shadowy rivers of the Cretaceous world, it was the undisputed king, a terrible crocodile whose legacy survived in stone until curious eyes uncovered its secrets. When the very first broken and scattered bones that would later be recognized as belonging to Deinosuchus were discovered, scientists quickly noticed its similarity to crocodiles. Because of this, in the year 1954, researchers decided to place it in the crocodile family, known scientifically as Crocodilidae. This classification was based mostly on the shape and details of its teeth, which at the time seemed like the strongest clue to its true identity. However, the story did not end there. Decades later, in the year 1999, new fossil discoveries in Texas and Georgia changed the scientific picture. These new bones provided researchers with more information, enough for them to carry out a detailed phylogenetic analysis, a study of evolutionary relationships. The results of this analysis shifted Deinosuchus out of the crocodile family and placed it in a more primitive or basal position, within the group known as Alligatoridae. This was the same group that contained another ancient animal called Deinosuchus. In other words, Deinosuchus was now seen as being more closely related to alligators than to crocodiles. This updated classification gained even more support in the year 2005, when a remarkably well-preserved skull fragment, a brain case, of Deinosuchus was uncovered in the Blufftown Formation of Alabama. This fossil showed certain details that reminded paleontologists of the skull structure of the modern American alligator. Even so, scientists were careful to point out that Deinosuchus was not a direct ancestor of today's alligators. Instead, it was more like a distant cousin that shared some family traits without being part of the direct line leading to the living species. Over the years, the exact classification of the different species within the genus Deinosuchus has been debated. Since the name Deinosuchus was formally brought back into scientific use in the year 1979, paleontologists have typically recognized two main species. The first, Deinosuchus rugosus, was thought to have lived in Appalachia, the ancient landmass that once formed the eastern part of North America. The second group, known as Deinosuchus hatcheri, or Deinosuchus riograndensis, lived in Laramidia, the western landmass of North America, and was believed to be larger. These supposed differences were often based on variations in the size, shape, and surface texture of their osteoderms, the bony armor plates in their skin, and their teeth. Yet, as time went on and more fossils were compared, it became clear that the differences between these groups were not always sharp enough to separate them into distinct species. Other than size, they appeared to share most features in common. Because of this, many scientists began to think that these supposed species might actually all belong to the same one after all. In the year 2013, paleontologist Randall Ermis and his colleagues carried out a careful review of crocodiliform fossils from the Kaparowitz Formation in Utah. They pointed out that the species Deinosuchus rugosus was questionable because its original specimen, or holotype, consisted only of teeth that were not distinctive enough to properly diagnose a species. Because of this, they suggested that fossils from Laramidia should be referred to as Deinosuchus hatcheri. They also emphasized that fossils from Appalachia, especially skull material, had not yet been fully described, leaving the picture incomplete. Then, in the year 2020, paleontologists Alan Cossette and Christopher Brochu took another close look at the situation. They agreed that Deinosuchus rugosus was too poorly defined, and its type material too undiagnostic, making it a nomen dubium, a dubious name in scientific terms. To address this, they created a new species, Deinosuchus schwimmeri, named in honor of fellow paleontologist David R. Schwimmer. This new species included several specimens that had previously been assigned to Deinosuchus rugosus and represented the Appalachian population. Cossette and Brochu also re-examined the type specimen of Deinosuchus hatcheri, which was incomplete but had certain unique features. For example, the edges of its indented osteoderms had a particular shape not seen in other species. Yet even this was not entirely reliable, because it was possible that the fossils of the other species had simply not been preserved well enough to show the same detail. Because of the incomplete nature of the original type specimen of Deinosuchus hatcheri, Cossette and Brochu suggested an important change. They proposed transferring the official type species designation to Deinosuchus riograndensis, which had much better preserved fossils. This move, they argued, would make it easier for scientists to properly identify and distinguish between different Deinosuchus species. As for its broader evolutionary relationships, phylogenetic analyses continued to place Deinosuchus as a basal member of the Alligatoridae group, showing it as part of the branch that eventually led to alligators but not directly in their line. Yet even this view did not remain fixed. In the year 2025, researcher Jules D. Walter and his team published a new study that once again challenged older ideas. They argued that many of the traits once thought to be unique identifiers of alligatoids were actually much more widespread among different crocodile-like reptiles. According to their analysis, several ancient genera traditionally considered to be early alligatoids, including Deinosuchus, did not belong within Alligatoridea at all. In fact, they might not even have been true crocodilians. Instead, they appeared to belong to a group of advanced Eusuchians, reptiles closely related to crocodiles and alligators, but not part of the modern crocodilian family. In Walter's study, Deinosuchus was shown to have branched off from the evolutionary line leading to true crocodilians after the appearance of Deinosuchus, but before the rise of another group known as Planocranidae, which lived more on land. This new finding placed Deinosuchus in a unique position on the evolutionary tree, separate from the ancestors of both crocodiles and alligators, and highlighted just how unusual and important this giant reptile was in the grand history of crocodilian evolution. Even though Deinosuchus was enormous, truly one of the giants among prehistoric crocodilians, its overall look was surprisingly similar to the crocodiles and alligators we see today. Its snout was broad and rounded, much like that of a modern alligator, but with a slightly swollen, bulbous tip that gave it a distinct, almost powerful presence. On the very front of the upper jaw, the premaxilla, it had 4 teeth. Interestingly, the 2 teeth closest to the tip of the snout were noticeably smaller than the other 2, creating a subtle but important difference in its bite pattern. Moving further back along the upper jaw, the main tooth-bearing bone called the maxilla contained 21 or 22 teeth, each thick and robust, built more for crushing than slicing or piercing. The lower jaw, anchored by the dentary bone, held at least 22 teeth as well. Towards the back of the mouth, these teeth became short, blunt, and rounded, perfectly adapted for crushing hard-shelled prey such as turtles or armored dinosaurs. When Deinosuchus closed its mouth, only a single tooth, the 4th one in the lower jaw, would peek out, giving it a slightly fearsome grin. The skull of Deinosuchus was unlike that of any other crocodilian, whether living or extinct. While broad like an alligator's, the front of the skull around the nostrils or nares was slightly inflated, giving it a unique profile. In front of the nares, the premaxilla contained 2 holes that are not seen in any other crocodilian. These peculiar features, called autapomorphes, remain a mystery, and scientists are still unsure what purpose they served. When it came to raw power, Deinosuchus was a true heavyweight. To put this into perspective, the modern saltwater crocodile, Crocodylus porosus, holds the record for the strongest bite of any living animal. One individual measuring 4 meters and 59 centimeters, weighing 531 kilograms, could bite with a force of 16,414 newtons, which equals 1,673 kilograms of force, or 3,690 pounds. Deinosuchus, however, far exceeded even this, with estimates for its bite force ranging from 18,000 newtons, equal to 1,835 kilograms of force, or 4,047 pounds, to an astounding 102,803 newtons, which translates to 10,483 kilograms of force, or 23,111 pounds. Its jaws were true engines of destruction, capable of crushing almost anything unfortunate enough to cross its path. Deinosuchus also had a secondary bony palate, a feature that allowed it to breathe through its nostrils even while its entire head remained underwater. This meant it could lie in wait, mostly submerged, and still breathe without revealing itself. Its vertebrae were procoelous, meaning the front of each vertebra was hollow and concave, while the back end was convex and bulging. This ball and socket-like arrangement allowed for greater flexibility and strength in the spine, similar to what is seen in modern Eusuchian crocodilians. Both the secondary palate and procoelous vertebrae are advanced traits that highlight how Deinosuchus shared key evolutionary innovations with its modern relatives. Covering its back were enormous heavy osteoderms, or bony scutes, many of them roughly hemispherical and deeply pitted. These pits and grooves provided strong attachment points for connective tissues, creating a sort of natural armour. Together, the osteoderms and connective tissues would have reinforced Deinosuchus' massive frame, supporting its weight on land as well as in water. The sheer depth of the pits on these osteoderms has led scientists to believe that despite its immense size, Deinosuchus could probably move across land in a way similar to today's crocodiles, walking with a surprising degree of agility for such a giant predator. In every detail, from its bulbous snout to its crushing teeth, from its armoured back to its powerful bite, Deinosuchus combined features of modern crocodilians with unique adaptations of its own, making it one of the most formidable and fascinating reptiles ever to roam the late Cretaceous rivers and coastlines. Even though the fossil remains of Deinosuchus are often incomplete and scattered, scientists have long recognised that this prehistoric reptile was truly enormous. Over the decades, paleontologists have tried to understand just how immense it was, but the estimates have changed considerably as new discoveries and methods have come to light. The early ideas about its size were based on very limited material, which left room for considerable speculation. The story of Deinosuchus' size begins with the first detailed study of fossils that were later attributed to this giant crocodile. Back in the year 1954, researchers examined a type specimen that at the time had been given the name Phobosuchus riograndensis. The scientist had only a partial skull, which measured 1.5 meters, and a lower jaw that stretched 1 8/10 meters in length. To estimate the total length of the animal, they compared these fossils to the modern Cuban crocodile, assuming similar proportions. Using this method, they concluded that the creature could have reached a staggering total length of 15 meters, which is just over 49 feet. To put that in perspective, 15 meters is roughly as long as a standard school bus parked end to end. However, as paleontology advanced and more complete fossils were discovered, this original reconstruction came under scrutiny. Today, that 15-meter estimate is generally regarded as an overstatement, primarily because the method of scaling from modern crocodiles failed to account for the unique proportions of Deinosuchus. The first significant re-evaluation of Deinosuchus' size came many decades later. By the end of the 20th century, more complete fossil specimens had been discovered, particularly from sites in the southern United States such as Texas and Georgia. With these additional remains, paleontologists could make more accurate reconstructions. In the year 1999, it was estimated that the typical size of Deinosuchus specimens ranged from 8 to 10 meters in length, or roughly 26 to 33 feet. The weight of these massive reptiles was estimated between 2.5 to 5 metric tons, which translates to approximately 2 8/10 to 5.5 short tons. This was an enormous animal, far larger than any crocodilian alive today, but not quite as long as the early 15-meter estimates had suggested. Further studies helped refine these estimates. Most known specimens of Deinosuchus rugosus, the species most commonly represented in the fossil record, usually had skulls measuring around 1 meter in length, equivalent to about 3 1/3 feet. Based on the proportions of these skulls, the total body length was estimated at about 8 meters, or 26 feet, with a weight of approximately 2 3/10 metric tons, roughly 2.5 short tons. These calculations suggested that while D. rugosus was enormous, it was slightly smaller than earlier, more speculative reconstructions had claimed. One particularly well-preserved skull discovered in Texas offered even more insight into the size of Deinosuchus. This skull measured about 1 meter and 31 centimeters, or roughly 4 1/3 feet in length. Using the proportions of this skull, scientists estimated that the animal's total body length could have reached 9 meters and 80 centimeters, which is about 32 feet. This individual, therefore, would have been among the larger specimens known, and its discovery helped researchers understand the true scale of this prehistoric predator. The question of the largest individuals of Deinosuchus has always fascinated paleontologists. In the year 2002, a researcher named Schwimmer proposed that the largest specimens of D. riograndensis could have reached lengths of up to 12 meters, or 39 feet. This is approximately 1.5 times the average length of D. rugosus. Schwimmer's estimates were based on detailed measurements of vertebrae from type specimens of Phobosuchus riograndensis and Deinosuchus hatcheri. By scaling these vertebrae proportionally, he suggested that the largest individuals might have weighed nearly 8.5 metric tons, or about 9 4/10 short tons. More recent studies have offered slightly different estimates, reflecting improvements in methods for measuring size from fossils. In the year 2020, researchers Ijima and Kubo re-evaluated the type specimen AMNH 3073 using regression equations based on modern crocodilians. because crocodilian vertebrae scale with positive allometry, meaning that larger animals' vertebrae grow disproportionately larger than smaller ones. Simple linear scaling can overestimate size. Their calculations suggested that this specimen would have measured between 7 meters and 37 centimeters to 8 meters and 17 centimeters in length, or roughly 24 to 27 feet. This more conservative estimate illustrates the challenges paleontologists face when attempting to reconstruct the size of an animal known only from fragmentary remains. A particularly interesting specimen is a large fragment of the lower jaw, or mandible, from D. riograndensis. Based on the size of this fragment, scientists estimated that the individual it belonged to had a skull measuring 1 meter and 47.5 centimeters, which is about 4 8/10 feet. Using a regression equation derived from the relationship between skull length and total length in the modern American alligator, researchers estimated that this animal could have reached a total length of 10 meters and 64 centimeters, or approximately 34 feet and 9 inches. This estimate is only slightly lower than earlier suggestions for the maximum size of this species, further reinforcing the idea that Deinosuchus was one of the largest crocodiliforms to have ever existed. Deinosuchus has often been described as the largest crocodiliform of all time, a label that captures the imagination because it evokes images of rivers and coastal waters dominated by a predator far larger than any living crocodile. However, it is important to recognize that other prehistoric crocodiliforms may have rivaled or even exceeded it in size. Among these are Purosaurus, a giant crocodilian from South America, Griposuchus, a long-snouted relative from the Miocene of South America, Ramphosuchus, a huge crocodilian from India, Euthecodon, an African crocodiliform with formidable size, and Sarcosuchus, the supercroc of the early Cretaceous of Africa. Each of these animals reached impressive lengths and masses, suggesting that Deinosuchus was part of a broader pattern in which crocodiliforms periodically evolved to enormous sizes, often dominating the ecosystems they inhabited. The diversity in estimates for Deinosuchus' size highlights several important points about paleontology. First, reconstructing the size of extinct animals is always challenging, particularly when only fragmentary remains are available. Researchers must rely on comparisons with living relatives, proportional scaling, and increasingly sophisticated mathematical models to make their best guesses. Over time, these methods have become more precise, but they still leave room for debate. Second, Deinosuchus' size may have varied significantly within the genus. Like modern crocodiles, some individuals were relatively small, while others reached truly monstrous proportions. Finally, discoveries of new specimens continue to refine our understanding, illustrating how scientific knowledge is always evolving. Fossils of Deinosuchus have also been instrumental in understanding growth patterns in prehistoric crocodiliforms. By comparing the sizes of skulls, jaws, and vertebrae from multiple individuals, researchers can estimate how quickly these animals grew, how long they lived, and how their body proportions changed with age. For example, the exceptionally large specimens suggest that some individuals lived long enough to reach enormous sizes, potentially over several decades, much like the largest modern crocodiles. Understanding these growth patterns helps paleontologists paint a more complete picture of Deinosuchus' life history, from juvenile stages to fully grown adults. The debate over the larger size of Deinosuchus also underscores the differences between species within the genus. D. rugosus, which is well represented in the fossil record, appears to have been slightly smaller on average than D. riograndensis, though both species were massive compared to modern crocodiles. The skull measurements and vertebral scaling suggest that the largest D. riograndensis individuals may have exceeded 12 meters in length, whereas most D. rugosus specimens were closer to 8 or 9 meters. These distinctions highlight the variability within the genus and suggest that different species may have occupied slightly different ecological niches, with size playing a role in hunting strategy, prey selection, and territorial behavior. In addition to body length and weight, researchers have studied specific fossil elements to refine size estimates. Mandibular fragments, skulls, and vertebrae all provide clues, and each fossil can tell a slightly different story. By comparing these measurements with modern crocodilians, paleontologists can apply regression equations to estimate total body size. These techniques, while not perfect, offer a way to move beyond simple speculation and produce data-driven estimates that reflect the unique biology of Deinosuchus. Such methods have led to the recognition that while early estimates of 15 metres were likely too large, a length of 10 metres or slightly more for the largest individuals is plausible and supported by multiple lines of evidence. However, the recognition of Deinosuchus as one of the largest crocodiliforms ever known has captured the public imagination. From museum exhibits to documentaries, this massive predator embodies the incredible diversity and scale of prehistoric life. Its size, power, and role as a top predator make it a symbol of the late Cretaceous waterways, where enormous reptiles coexisted with dinosaurs and other ancient creatures. By studying Deinosuchus, scientists gain not only a window into the past, but also a deeper appreciation for the evolutionary processes that allowed crocodilians and their relatives to achieve such remarkable sizes over millions of years. In the year 1954, the renowned paleontologists Edwin H. Colbert and Roland T. Bird put forward a remarkable idea about Deinosuchus, the gigantic prehistoric crocodile. They suggested that this enormous reptile may very well have hunted and devoured some of the dinosaurs with which it was contemporaneous. This was not a casual guess. It reflected the understanding of Deinosuchus as an apex predator, a creature so massive that it likely exerted a dominant influence over its ecosystem. 7 years later, in 1961, Colbert returned to the topic with even greater confidence. He stated that, "Certainly this crocodile must have been a predator of dinosaurs. Otherwise, why would it have been so overwhelmingly gigantic? It hunted in the water where the giant theropods could not go." This was an important assertion, highlighting the idea that Deinosuchus's sheer size was not arbitrary. It had evolved to overpower formidable prey, including dinosaurs that roamed the lands near rivers and lakes during the late Cretaceous period. The theory that Deinosuchus occasionally hunted dinosaurs was later supported by more concrete evidence. In the year 2002, paleontologist David R. Schwimmer presented findings that reinforced this idea. He observed that several hadrosaurid tail vertebrae discovered near what is today Big Bend National Park in Texas bore unmistakable bite marks. These marks matched the teeth of Deinosuchus, suggesting that the enormous crocodile had, at least occasionally, fed on dinosaurs. Schwimmer's research lent credence to the long-standing speculation, bridging the gap between theoretical predictions and fossil evidence. A year later, in 2003, Christopher A. Brochu, another respected expert on crocodilians, concurred, noting that Deinosuchus probably dined on ornithopods from time to time. This statement confirmed that the diet of Deinosuchus was not limited to small or weak prey. Rather, it could include medium-sized dinosaurs, adding a layer of complexity to our understanding of late Cretaceous food webs. Scientists have long believed that Deinosuchus hunted in ways similar to modern crocodilians. Like today's alligators and crocodiles, it would have likely waited patiently at the water's edge, hidden beneath the surface, until unsuspecting dinosaurs or other terrestrial animals came close enough. Then, with a sudden burst of strength, it would seize them, dragging them into the water to drown. This ambush method was highly effective and required both stealth and enormous physical power. A study conducted in the year 2014 even suggested that Deinosuchus was capable of performing a death roll, a vicious spinning maneuver observed in modern crocodiles that helps subdue and dismember prey. This ability would have made Deinosuchus an even more fearsome predator, capable of dealing with struggling prey far larger than those typically handled by today's crocodiles. Further supporting evidence came from an analysis conducted by Schwimmer in the year 2010. He noted that a tyrannosauroid leg bone, labelled NJSM 13096, housed in the New Jersey State Museum and recovered from the Ellisdale fossil site, displayed distinct bite marks. These marks were consistent with the teeth of Deinosuchus, providing additional proof that the giant crocodile did not shy away from targeting dinosaurs, even those with formidable defences. This finding underscored the idea that Deinosuchus occupied the top of its ecological hierarchy, preying on creatures that might otherwise have been considered untouchable. However, Deinosuchus's diet was not limited to terrestrial animals. In 1996, Schwimmer, together with G. Dent Williams, proposed that Deinosuchus may also have preyed upon marine turtles. These turtles were abundant in the Cretaceous waterways and had shells that could be crushed by the powerful jaws of the giant crocodile. The back teeth of Deinosuchus were broad, flat, and ideal for crushing hard shells, allowing it to feed on creatures that other predators might have ignored. One particularly common type of turtle in the eastern habitats of Deinosuchus was the side-necked sea turtle Bothromes. Fossilized shells of Bothromies have been discovered with bite marks that almost certainly belong to Deinosuchus, further illustrating its versatility as a predator and its ability to exploit a variety of food sources. Schwimmer's research in the year 2002 suggested that the feeding habits of Deinosuchus likely differed depending on geographic location. In eastern North America, where smaller specimens of Deinosuchus have been found, the crocodile probably lived as an opportunistic feeder, much like modern American alligators. These smaller individuals would have hunted a mix of marine turtles, large fish, and smaller dinosaurs, taking advantage of any food source that came within reach. In contrast, the larger and more rare Deinosuchus specimens discovered in Texas and Montana likely pursued a more specialized diet. These massive crocodiles were capable of capturing and consuming large dinosaurs, dominating the local ecosystem as apex predators. In the eastern range, no theropod dinosaurs approached the size of Deinosuchus, which indicates that this crocodilian occupied a unique niche, reigning supreme over its territory without competition from other large predators. Growth patterns of Deinosuchus provide further insight into its lifestyle and ecological impact. In 1999, a study conducted by Gregory M. Erickson and Christopher A. Brochu examined growth rings in the dorsal osteoderms, or bony plates, of various Deinosuchus specimens. Their findings suggested that the growth rate of Deinosuchus was similar to that of modern crocodiles, but extended over a much longer period. Estimates indicated that each Deinosuchus might have required more than 35 years to reach full adult size, with the oldest individuals potentially living for over 50 years. This long and steady growth was fundamentally different from the rapid growth and shorter lifespans observed in large dinosaurs. Erickson highlighted the profound implications of this longevity, noting that a full-grown Deinosuchus must have seen several generations of dinosaurs come and go. Unlike the large theropods or herbivorous giants that matured quickly and died relatively young, Deinosuchus could persist in its environment for decades, witnessing the ebb and flow of prehistoric life around it. Nevertheless, Schwimmer cautioned in 2002 that the interpretation of growth rings in Deinosuchus osteoderms was not entirely straightforward. The analysis by Erickson and Brochu assumed that each ring represented 1 year, as is the case with modern crocodiles. However, Schwimmer noted that the formation of these rings could have been influenced by numerous environmental and biological factors, such as seasonal fluctuations between wet and dry periods, migrations of prey, or changes in oceanic circulation and nutrient availability. If the rings actually reflected a cycle of 2 years rather than 1, it could imply that Deinosuchus grew faster than modern crocodilians, potentially reaching adult size more quickly, while maintaining a comparable maximum lifespan. This uncertainty highlights how even the most detailed fossil evidence must be interpreted carefully, as the biology of extinct animals can never be reconstructed with absolute certainty. Taken together, the evidence paints a picture of Deinosuchus as a remarkably adaptable and formidable predator. It was capable of hunting both terrestrial and aquatic prey, including dinosaurs, turtles, and large fish. Its hunting strategy relied on a combination of patience, stealth, and sheer physical power, allowing it to ambush prey at the water's edge and submerge it until death. Its slow, extended growth and long lifespan gave it a sustained presence in its environment, dominating food chains across multiple generations. While smaller eastern populations may have been opportunistic feeders, taking advantage of whatever prey came near, the larger individuals in regions such as Texas and Montana were specialized hunters, capable of subduing creatures that would have been dangerous or unmanageable for other predators. The fossil record from bite-marked bones to crushed turtle shells supports this interpretation, offering glimpses into a life that was both brutal and efficient. Deinosuchus's ability to perform maneuvers such as the death roll, combined with its crushing bite force, would have made it a terrifying predator in any context. Unlike most large dinosaurs, which reached their massive sizes in a relatively short span of years, Deinosuchus took decades to grow, allowing it to develop an unmatched combination of size, strength, and experience. Each generation of dinosaurs that lived alongside it may have known the presence of this giant crocodile as an ever-present threat, shaping behaviors, migration patterns, and even survival strategies in the surrounding ecosystem. Deinosuchus lived on both the eastern and western sides of what was once known as the Western Interior Seaway, a vast inland sea that split North America during the late Cretaceous period. Fossils of this giant reptile have been discovered across a remarkable 12 modern-day states in the United States. These states include Utah, Montana, Wyoming, New Mexico, New Jersey, specifically within the Marshalltown Formation, Delaware, Georgia, Alabama, Mississippi, Texas, and both North and South Carolina, where fossils have been found in formations known as the Tar Heel, Coachman, and Blodden formations. In addition to these, a single osteoderm, a bony plate from Deinosuchus, was reported in the San Carlos Formation in 2006, suggesting that the range of this giant crocodilian may have extended into northern regions of what is now Mexico. There is also a report of a possible Deinosuchus scute from the state of Colorado, although it remains less certain. Among all these locations, the Gulf Coastal Plain, particularly in Georgia near the border with Alabama, appears to have been a hotspot for Deinosuchus fossils. This abundance suggests that the region may have been a favoured habitat for the giant predator. All known remains of Deinosuchus have been found in rocks that are dated to the Campanian stage of the late Cretaceous period, a span of time that stretches roughly from 82 million to 73 million years ago. This means that the earliest members of this genus appeared about 82 million years ago, while the most recent lived approximately 73 million years ago, surviving nearly 10 million years through a dynamic and changing landscape. The locations and types of fossil deposits indicate that Deinosuchus likely preferred environments such as estuaries, where rivers met the sea, creating a mix of fresh and salt water. In the Aguja Formation of Texas, where some of the largest specimens have been unearthed, these colossal predators probably lurked in brackish water bays, hunting whatever prey came within reach. While a few fossils have been found in marine deposits far from shore, it is unclear whether Deinosuchus actively ventured into the open ocean like modern saltwater crocodiles. These marine finds could instead represent individuals that were carried out to sea after death, their remains drifting with currents before being buried and fossilized. Overall, Deinosuchus has been described as a conspicuous and highly noticeable member of a distinct biome that dominated the southern portion of late Cretaceous North America, highlighting its significance in the ancient ecosystem. Interestingly, the presence of Deinosuchus may have shaped the balance of predators in its environment. Some paleontologists have suggested that this giant crocodilian could explain why very large predatory theropod dinosaurs are rare in the fossil record of late Cretaceous Appalachia. Essentially, Deinosuchus may have taken on the role of the top predator in the coastal plains of this region, filling the ecological niche that, in other regions, might have been occupied by massive meat-eating dinosaurs. Its sheer size, power, and dominance in estuarine and coastal habitats likely allowed it to control local food chains, making it one of the most formidable predators of its time. Arthroplura is one of the most fascinating and gigantic creatures ever to walk the land. It is an extinct genus of enormous myriapods, a group of arthropods that today includes millipedes and centipedes, but Arthroplura far surpassed anything alive now in sheer size. This extraordinary creature lived during a vast stretch of time that began around 344 million years ago, during a period known as the Visian stage of the Lower Carboniferous, and persisted until approximately 292 million years ago, in the Sackmarian stage of the early Permian period. In simpler terms, Arthroplura existed hundreds of millions of years before the age of the dinosaurs, roaming ancient landscapes long before the world looked anything like it does today. From the fossils and traces that scientists have discovered, it is clear that Arthroplura was truly a giant among land-dwelling arthropods. Estimates suggest it could reach lengths of at least 2 meters, which is roughly 6 feet and 7 inches, and in some cases, it may have even grown to over 2.5 meters, or 8 feet and 2 inches. To put that into perspective, imagine a creature longer than most modern dining tables crawling across the forests of ancient Europe and North America. No land arthropod, either living or extinct, comes close to matching the sheer magnitude of Arthroplura. The evidence for its size and existence comes not only from fragments of its body preserved in fossils, but also from giant trackways, essentially fossilized footprints, measuring up to 50 centimeters or 20 inches across. Some of these tracks are so massive that they provide a clear picture of just how enormous and heavy this creature must have been. There is also speculation that Arthroplura might have created large burrows, further hinting at its interaction with the environment and possibly its behaviour. Arthroplura inhabited open, lightly wooded environments near water, where the ground would have been damp and soft, ideal for such a massive arthropod to move about. Scientists have debated whether it might have been amphibious, capable of spending time both on land and in shallow water. Its habitat millions of years ago was dominated by coal swamps and river systems, providing a humid and rich environment where giant plants and other arthropods thrived. The combination of soft soil, abundant vegetation, and high humidity would have allowed Arthroplura to grow to its remarkable size, feeding on the plentiful resources around it. The story of Arthroplura's discovery begins in the mid-19th century. In the year 1849, during the construction of a railway near a place called Friedrichsthal, in what is now Germany, workers uncovered some of the first remains of this remarkable creature. From the very beginning, Arthroplura captured the imagination of both scientists and artists alike. Despite the excitement, the remains were mostly fragmentary, meaning that researchers had only small parts of the creature to study, which made understanding its anatomy and lifestyle a complex challenge. Initially, the German paleontologist Hermann von Meyer misidentified these early remains. He believed that Arthroplura armata, as he called it, was not a millipede or any kind of myriapod, but instead a massive crustacean related to decapods, which include modern crabs and lobsters. He noted that the exoskeleton of the creature had body rings, which he called pleura and rachis, and these seemed to form separate parts. In his view, the creature's segments were unlike anything else known, and he expressed amazement at the unusual and remarkable nature of the fossil. Von Meyer's description was both detailed and cautious, reflecting the uncertainty of early paleontology, a time when scientists were still learning how to interpret fossils accurately. Later, Hermann Jordan and Hermann von Meyer revisited Arthroplura and compared it to other ancient arthropods, including trilobites and eurypterids, sometimes called sea scorpions. It was during this period that the name Arthroplura was formally established, with its meaning jointed rib, referring to the structure of its armor-like exoskeleton. The central ridge along its back, known as the rachis, was separated from the side plates, or paratogites, in a way reminiscent of ribs, giving the creature a distinctive segmented appearance. As research continued, another scientist, Moritz Kleiver, described a smaller specimen of Arthroplura armata, focusing on the underside of the creature. He observed 7 pairs of limbs attached to various plates, including the sternites, which are the ventral plates of arthropods. Kleiver proposed that Arthroplura was neither an insect nor an arachnid, nor even a traditional myriapod. Instead, he argued, it might be a non-decapod crustacean, comparing its appendages to those of brachiopods, small freshwater crustaceans. For several decades, some researchers continued to link Arthroplura with crustaceans, particularly primitive isopods and other early relatives. It was not until 1911 that paleontologists Louis Moissey and Henry Woodward made a significant breakthrough by associating Arthroplura with myriapods, bringing it into the same lineage as millipedes. This interpretation gradually became more widely accepted, especially as more fossil evidence came to light, allowing scientists to better understand the creature's limbs and general anatomy. In 1934, a landmark study by Gérard Wattelau established the order Arthropluridae, formally placing Arthroplura within a broader taxonomic framework. Waterlot initially suggested that Arthroplura's limbs were biramous, meaning each limb had 2 branches, one for walking and one functioning as a gill, similar to trilobites. However, a decade later, in 1944, paleontologist Leif Sturmer challenged this idea after examining photographs of the fossils. He noted that the supposed 2 branches of each limb were always positioned very close together, so close that even their joints aligned perfectly, indicating that the limbs were aneurymous, having only a single branch. This careful observation helped refine the understanding of Arthroplura's anatomy and provided clearer insight into its movement and behaviour. Waterlot had also studied a nearly complete juvenile specimen described by Dr. W. T. Kalman, which he called Arthroplura moysaei, although he considered it part of the species Arthroplura armata. This juvenile fossil provided critical information about the head, a segment of the animal that had remained mostly unknown. Waterlot identified a curved structure along the edge of the head that resembled the mandibles of some myriapods, suggesting it was a cephalic feeding appendage. Based on this, he hypothesized that Arthroplura was carnivorous, feeding on small, soft-bodied animals. He also proposed that the creature was amphibious, living at the bottom of ancient lake beds and occasionally venturing onto land, where the humid conditions of coal swamps would have helped it continue breathing through gill-like structures. However, Not all scientists agreed with Waterlot's interpretation. Some argued that Arthroplura was primarily terrestrial, walking on land rather than spending significant time in water. They also questioned whether it was truly carnivorous. The juvenile specimen Waterlot studied appeared to show plant material inside its gut, although modern researchers now think this may have been a taphonomic artifact, meaning the plant remains were deposited during fossilization rather than being actual food. The most complete known adult specimen of Arthroplura, known as the Maybach specimen, was described by Paul Guthurl in 1935. It was discovered in the roof of a German coal mine and carefully extracted, measuring 90 centimeters or 35 inches in length. Although this specimen was smaller than some of the estimated giant individuals, it provided an invaluable view of the adult morphology and confirmed many features suggested by earlier fragmentary remains. Over the decades, the classification of Arthroplura as a myriapod, or at least a relative of myriapods, particularly diplopods, which include modern millipedes, became the prevailing view among scientists. The limbs, which had been a source of debate for decades, gradually became well understood, showing a structure consistent with other large myriapods. Further species of Arthroplura were described over time, mostly from Central Europe and the United Kingdom, and even from parts of the central United States, including Arthroplura cristata. North American evidence comes not only from fossilized remains but also from widespread giant trackways, along with fossils found in Nova Scotia, Ohio, and Pennsylvania, indicating that these enormous arthropods were once distributed across a broad geographic range. Despite all the progress in understanding Arthroplura, the head segment remained a mystery even into the 21st century. Earlier researchers had misidentified what they thought was the head. This segment was later recognized as the column, which is the first segment behind the true head. The actual head remained hidden beneath it, a tiny and often overlooked structure. A breakthrough came in 1999 with the description of a tiny Devonian millipede named Microdeiemplex, believed to belong to the same subclass, Arthropluridae. This small and exceptionally well-preserved fossil provided detailed information about the head anatomy of these ancient myriapods. By studying Microdeiemplex, scientists gained new insight into the structure of Arthroplura's head, filling in a critical gap in the understanding of this giant arthropod. In the year 2024, an extraordinary discovery was made in the fossil-rich Monceau-les-Mines-Lagastette of France. Researchers, using advanced micro-CT scanning technology, studied and described two nearly complete juvenile fossils of Arthroplura, revealing for the first time in remarkable detail the structure of their head regions. These scans confirmed what earlier scientists had long suspected. The part previously identified as the head truly was the head, and immediately behind it lay the column, a thin, distinct segment. What had once been interpreted as cephalic limbs by Waterlot were now understood to be paired ventral sclerites, armoured plates situated below the head that functioned almost like a protective car bumper. Further examination of these cephalic structures revealed that Arthroplura possessed two pairs of external maxillae, the mouth parts on the outside, and an internal set of mandibles, the biting organs inside the mouth. Phylogenetic analysis, which studies the evolutionary relationships between species, placed Arthroplura just outside the crown group of modern millipedes, classifying it as a stem group Diplopoda, whereas another genus, Microdeiemplex, was positioned as a true crown group millipede, rather than a member of the Arthropluridean lineage. The larger of the two exceptionally preserved juvenile fossils from Monceau-les-Mines displayed the head with its antennae and stalked eyes, as well as the trunk adorned with legs, two pairs on each body segment. The smaller fossil, though more diminutive, also preserved the head in vivid detail, including the delicate structures of the antennae and eyes. Together, these fossils allowed scientists to study the intricate anatomy of these ancient giants like never before. Beyond these exceptional specimens, many partial fossils and trackways suggest that Arthroplura could reach truly enormous sizes, growing longer than 2 meters, which is approximately 6 feet and 7 inches. At Joggins, Nova Scotia, trackways as wide as 50 centimeters, about 20 inches, have been documented, indicating the staggering breadth of their bodies. In 2021, a particularly notable fossil was reported, likely representing a shed exoskeleton, or exuviae, of an Arthroplura. Though the exact species could not be determined, as only the underside of the carapace was preserved, its estimated width was 55 centimeters, or 22 inches, with a length ranging between 1.9 metres and 2.63 metres, or roughly 6 feet 3 inches to 8 feet 8 inches, and a body mass of around 50 kilograms, or 110 pounds. These measurements place Arthroplura among the largest arthropods ever known, comparable in size to the enormous Eurypterid Ecological Rhenaniae, estimated at a length between 2.33 and 2.59 metres, or roughly 7 feet 8 inches to 8 feet 6 inches. The 2024 study provided further insights by describing the complete head and trunk of a juvenile Arthroplura specimen from the Casimovian stage, approximately 305 million years ago. This revealed several previously unknown anatomical details. The head bore a pair of long segmented antennae with at least 7 antennal articles at the very front. The trunk displayed 28 to 32 well-developed tergites, or dorsal exoskeleton plates, each with a 3-lobed structure reminiscent of trilobites. The dorsal surfaces of these tergites were typically studded with numerous tubercles and spines, likely serving both protective and sensory functions. Juvenile individuals, by contrast, showed fewer tergites, typically between 20 and 24, indicating a hemianamorphic growth pattern. This meant that Arthroplura added new body segments during successive molts until reaching the adult number of segments, after which it continued to grow in size without adding further segments. Beneath the tergites, Arthroplura possessed pleurites, paired sclerites that lay between the sternite on the underside and the tergite on the dorsal side, running along either side of the body. These plates were positioned beneath the paratergites and above the legs, connected by flexible arthrodile membranes that allowed movement. Pleurites, observed in several fossils, including the famous Maybach specimen, appeared as oval-shaped plates with rough, grainy ornamentation. They likely served as attachment points for the trunk musculature, helping the animal coordinate the movement of its many legs and providing structural support to its enormous body. Arthroplura, one of the most astonishing creatures to have ever walked the earth, possessed an anatomy that revealed both its close relationship to millipedes and its own unique, almost alien adaptations. Beneath its massive head, it had not one but 2 pairs of specialized appendages called maxillae. Each of these appendages was made up of 3 distinct segments, known as podomeres, which allowed for flexibility and precise movement. Their design bore a remarkable resemblance to the mouthparts of modern centipedes. The outermost pair, which scientists refer to as the second maxillae, were relatively long, narrow and pointed, likely adapted for manipulating food or interacting with the environment. In contrast, the inner pair, called the first maxillae, were short, flat and plate-like, perhaps providing stability or acting as a surface against which food could be pressed and crushed. These specialized mouthparts, together with paired mandibles that were small, internalized and composed of 3 segments, gave Arthroplura a feeding mechanism that was closer to that of centipedes than to the millipedes we are familiar with today. Unlike the millipedes, whose mandibles are often more exposed or simplified, Arthropluras were completely tucked within the head capsule, highlighting a unique evolutionary adaptation within this extraordinary genus. Despite these similarities with centipedes, certain features unmistakably mark Arthroplura as a true relative of millipedes. For instance, the way its antennae and mandibles were segmented reflects classic millipede anatomy. Yet, it also displayed traits absent in modern species, such as a pair of legs positioned beneath the column, which is the first segment immediately behind the head. No millipede alive today carries legs in this position, making it a distinctive marker of Arthroplura as a sister group to the crown group of millipedes, a branch that diverged very early in millipede evolution. This mixture of ancestral and derived features illustrates how Arthroplura occupies a fascinating spot in the evolutionary tree. It is both a reflection of ancient millipedes and a pioneer of its own unique adaptations. One of the most remarkable features of Arthroplura was its visual system. Unlike any living myriapod, it possessed stalked compound eyes. These eyes, protruding from the head on stalk-like structures, would have allowed it to observe its surroundings in a manner completely foreign to modern millipedes and centipedes. While stalked compound eyes are known from the extinct stem myriapod group called Euthycarcinoidea, the eyes of Arthroplura appear to have evolved independently, representing a derived trait that arose separately from those seen in euthycarcinoids. This means that, despite some superficial similarity, Arthroplura's eyes were an evolutionary experiment of its own, tailored to meet the sensory demands of a gigantic ground-dwelling arthropod navigating dense carboniferous forests. The body of Arthroplura was equally fascinating and complex. Every segment along its elongated torso bore 2 pairs of walking legs. Each leg itself was composed of 9 or 10 segments, again providing remarkable flexibility and strength. Along each leg, a crease ran longitudinally, which likely served as an apodem, a kind of internal support structure allowing muscles to attach more efficiently. This ingenious structural adaptation would have been crucial for a creature of such enormous size, enabling its limbs to sustain the tremendous forces involved in locomotion. On the underside of each leg, paired sensory hairs, known as setae, were arranged along the segments, likely giving Arthroplura detailed tactile feedback from the ground. The leg's anterior surfaces were smooth, facilitating gliding movements through leaf litter or over logs, while the posterior surfaces were studded with tubercles and dotted with pores that housed even more sensory setae, enhancing the creature's ability to detect vibrations, obstacles, and prey in its environment. Beneath each pair of legs, there existed a sophisticated arrangement of ventral plates located alongside the central sternite. These plates were categorized into 3 types: K plates, B plates, and rosette plates. The function of these plates has been the subject of considerable debate among paleontologists. Some researchers initially suggested that either the K plates or the B plates served as respiratory organs, akin to primitive gills or tracheal structures, allowing Arthroplura to take in oxygen. This idea, however, was not universally accepted. In 1967, Rolf and Ingham proposed that all of these ventral plates were simply hardened sections of the exoskeleton, meant to strengthen and support the bases of the massive legs. In other words, they might have functioned as structural reinforcements, allowing such a large creature to walk without collapsing under its own weight. Later, in 1999, a paleontologist named Wilson offered a different interpretation. According to him, the K-plate was not merely a reinforcement, but a sac-shaped structure with a hollow interior. Its outer surface was covered in tiny pits adorned with setae, while the interior formed a reticulated network that may have facilitated respiration. In this scenario, the rhythmic movement of the legs could have helped pump hemolymph, the arthropod equivalent of blood, into and out of these hollow plates, effectively functioning as a breathing apparatus. The K-plates themselves were perforated with tubercles, possibly acting as spiracle-like openings into the internal respiratory structure. The rosette plates, divided into small triangular lobes, contained creases between the lobes that functioned as internal apodems, providing points for muscle attachment. The B-plate, on the other hand, may have been homologous to the coxa, the basal segment of the leg in other arthropods, and it was continuous with the rosette plate. Together, these plates allowed the legs to thrust backward and downward during movement, then return to their original positions, with relatively limited forward movement, giving Arthroplura a unique gait unlike any living creature. The posterior end of the body terminated in a small trapezoidal telson, which was covered in tubercles. Though modest in size, this tailpiece may have served multiple purposes, perhaps aiding in balance or providing additional attachment points for musculature. The combination of such specialized features, legs, ventral plates, and tail, demonstrates the extraordinary biomechanical ingenuity of Arthroplura. In terms of classification and species differentiation, the various species of Arthroplura are primarily distinguished by the ornamentation found on their dorsal plates, called tergites. Across all species, a central keel runs laterally along the tergites, and behind this keel, most species exhibit a line of large tubercles, small rounded projections that may have served both protective and display functions. One notable exception is Arthroplura cristata, known from the famous Mason Creek deposits in the United States, which entirely lacks this tuberculate ornamentation. However, the rarity of complete specimens makes it difficult for paleontologists to establish clear species boundaries. Some species may merely represent different growth stages of the same organism. For example, juvenile specimens from the Mont-Saint-Laurent Lagerstätte in France display a band of 4 prominent tubercles on the paratergal lobe, which rise into tall spine-like projections. This pattern closely resembles that of Arthroplura moisei, suggesting that A. moisei might also be a juvenile form, possibly of the larger species Arthroplura mammata. Because ornamentation changes with age, it is not considered a completely reliable method for identifying distinct species. The Mont-Saint-Laurent specimens also reveal interesting insights into the size variation of Arthroplura. Fossils from this site consist solely of juveniles, and the largest trackways indicate animals that were less than 50 centimetres in length, around 20 inches. This is remarkably small compared to the truly giant Arthroplura species known from other parts of Europe, which could grow to several metres in length. These observations suggest that some populations, particularly those from Mont-sur-le-Mine, may have been genuinely smaller, rather than simply representing juvenile stages of enormous adults. This variation in size hints at a complex ecological and evolutionary story, where different environments or time periods may have influenced the growth potential of these extraordinary arthropods. When considering the full anatomy of Arthroplura, from its complex mouthparts and specialized legs to its potential respiratory plates and unique visual organs, it becomes clear that this creature was unlike anything alive today. Its combination of features, internalized mandibles, dual pairs of maxillae, stalked compound eyes, 2 pairs of walking legs per segment, and a suite of ventral plates with potential respiratory and structural roles, paint a picture of a truly remarkable organism. Unlike modern millipedes or centipedes, which tend to be small, slow-moving, and relatively uniform, Arthroplura occupied a niche that required both strength and sensory sophistication, allowing it to navigate dense forests, avoid predators, and interact with the environment on a scale that is almost unimaginable. Most of the fossils we have of Arthroplura are thought not to be the remains of dead animals, but rather the exuviae, that is, the old shells left behind after the creature molted. Like many arthropods, Arthroplura would have shed its hard exoskeleton periodically as it grew, leaving behind a cast of its former body that could last millions of years under the right conditions. For a long time, scientists imagined Arthroplura wandering through dense coal swamps, reasoning this from the frequent discovery of its fossils alongside thick layers of plant debris and coal veins. These coal-rich forests, teeming with primitive plants, seemed like the perfect home for such a giant myriapod. However, as paleontologists continued to study its fossils and the environments in which they were found, this idea began to lose support. Many fossils appear either before or after the time when coal forests dominated the landscape, and careful examination of the surrounding rock layers and fossilized plants suggests that Arthroplura actually preferred much more open environments. It seems to have favored spaces that were lightly wooded, often near sources of water such as rivers, coastlines, and floodplains, rather than the deep, shadowy swamps once imagined. Fascinatingly, Arthroplura fossils are sometimes discovered alongside the tracks of early, four-limbed vertebrates called tetrapods, suggesting that these enormous arthropods and primitive land animals shared the same habitats. In addition to its famously large trackways, which record the passage of its immense body across ancient soil, enormous burrows have also been linked to Arthroplura and its relatives. Scientists think these burrows may have been dug during periods of estivation, a kind of arthropod hibernation, when the creature would slow down or retreat from harsh environmental conditions. Nearly all known Arthroplura fossils, including both body remains and trackways, have been found close to the ancient equator, within about 10 degrees north or south, during both the Carboniferous and the Permian periods, marking it as a true equatorial dweller. There has long been debate about whether Arthroplura could move in water as well as on land. For many years, the idea that it might have been at least partially amphibious fell out of favour, but more recent evidence has revived the hypothesis. Its trackways, often located near ancient coastlines, are found in sediments that were sometimes submerged and sometimes exposed, indicating that Arthroplura could walk in shallow water as easily as on dry ground. Additional support comes from exceptionally preserved juvenile fossils from Mont-sur-le-Mine in France, which reveal that the animal's eyes were large and perched on stalks, very unlike any living millipede or centipede. Similar features are seen in a group called Euthycarcinoidea, believed to be distant relatives of modern myriapods, which lived in both water and on land. This suggests Arthroplura may have been semi-aquatic, able to enter and exit shallow bodies of water with ease. Molting, the process of shedding and regrowing a new exoskeleton, was likely a critical and stressful period for Arthroplura, especially given its immense size. Some researchers propose that it may have undergone this process underwater, where the buoyancy of water could help support its heavy body while the new exoskeleton hardened. Others, like the paleontologist Wilson, argued that Arthroplura was mainly terrestrial and probably could not breathe underwater. She suggested that, like modern Scolopendra centipedes, it might have moved in a wriggling, worm-like fashion during molting, using its legs only after they had stiffened. Wilson also proposed that these giant arthropods could have molted inside burrows they dug themselves, although she remained open to the older idea proposed by Rolfe in 1985 that molting might have taken place inside hollow tree trunks of ancient lycopods. The naturally humid interior of these trees would have helped prevent the animal from drying out too quickly during this vulnerable period. The question of what Arthroplura ate has puzzled scientists for decades. Early researchers, such as Waterlot, thought it might have been a carnivore, feeding on smaller animals. However, the holotype of Arthroplura moisei, the first specimen used to describe the species, appeared to contain traces of woody plant material in its gut, suggesting a plant-based diet. Later research determined that these traces could not reliably be interpreted as stomach contents. Today, most scientists agree that Arthroplura was a detritivore, feeding on dead and decaying plant matter and possibly scavenging animal remains when available. Its short, tightly packed legs, combined with evidence from the shape and spacing of its trackways, indicate that Arthroplura moved slowly across the ancient landscape. Furthermore, the absence of venomous claws or other adaptations for hunting makes a predatory lifestyle highly unlikely. The enormous size of Arthroplura has often been linked to higher levels of oxygen in the atmosphere during the Carboniferous period, a time when oxygen concentrations were indeed significantly higher than today. Yet, this explanation does not fully match the fossil record or modern studies of arthropod growth limits. Remarkably, Arthroplura reached its giant sizes before oxygen levels peaked, with the largest known body fossil coming from a period when oxygen was only about 23% higher than present-day levels. It seems more plausible that the animal's gigantism was made possible by a combination of favourable environmental conditions, abundant resources, and a lack of major competition from other terrestrial creatures. Eventually, Arthroplura disappeared from the fossil record during the early Permian period. This extinction was likely driven by a combination of factors. The equatorial regions of the supercontinent Pangaea became increasingly arid, turning into deserts, and emerging tetrapod species may have competed with these massive arthropods for resources. In this way, a creature that had once dominated the warm, open landscapes near the ancient equator for tens of millions of years finally vanished, leaving behind only its tracks, burrows, and the occasional exuviae to hint at its former glory. Tyrannosaurus is a genus of enormous meat-eating dinosaurs known as theropods. The most famous species in this genus is Tyrannosaurus rex, with rex being Latin for king. People often shorten its name to T-Rex, or casually call it T-Rex. Among theropods, it is one of the best-known and most completely represented dinosaurs in the fossil record. Tyrannosaurus lived across what is now the western part of North America, which during the late Cretaceous period was an island continent called Laramidia. Unlike other tyrannosaurids, Tyrannosaurus had a far-reaching distribution. Its fossils appear in many different rock formations that date back to the very end of the Cretaceous period, specifically during the latest Campanian to Maastrichtian ages, from around 72,700,000 to 66 million years ago. Some isolated fossils hint that it might have first appeared a little earlier, in the Middle Campanian age. Tyrannosaurus was the last known member of the tyrannosaur family and one of the final non-bird dinosaurs to roam the Earth before the catastrophic Cretaceous-Paleogene extinction event wiped out nearly all dinosaurs. Like other members of its family, Tyrannosaurus was a bipedal predator, meaning it walked on two legs. Its enormous skull was balanced by a long, heavy tail that helped with stability. Compared to its massive and powerful hind legs, its forearms were quite short, yet they were unusually strong for their size and ended in two sharp, clawed fingers. The most complete Tyrannosaurus skeleton discovered measures about 12 meters, 3 centimeters to 12 meters, 4 centimeters in length, around 40 to 41 feet. Modern estimates suggest some individuals could have been even larger, reaching more than 13 meters or 43 feet in length, standing around 3 meters, 7 centimeters to 4 meters or 12 to 13 feet, tall at the hips, and weighing as much as 8 metric tons, which is roughly 8.7 long tons or 9.7 short tons. While a few other meat-eating dinosaurs might have matched or surpassed it in size, Tyrannosaurus remains one of the largest land predators ever known. Its bite force is estimated to have been the strongest of any animal that ever walked on land. Tyrannosaurus rex was by far the biggest predator in its environment. It likely hunted large herbivorous dinosaurs, including hadrosaurs, young or smaller armoured dinosaurs like ceratopsians and ankylosaurs, and perhaps even the long-necked sauropods. Some scientists have suggested that it might have been mostly a scavenger, feeding on the carcasses of dead animals. For decades, paleontologists debated whether Tyrannosaurus was a top predator, a scavenger, or a combination of both. Today, most experts agree that it was likely both a skilled hunter and an opportunistic scavenger, able to adapt its feeding strategy as needed. Several Tyrannosaurus rex fossils are nearly complete skeletons, which is rare among large dinosaurs. In at least one of these skeletons, researchers have even found soft tissues and proteins, a discovery that has revolutionized the study of dinosaur biology. Because so many fossils exist, scientists have been able to learn a great deal about Tyrannosaurus's life history, body mechanics, and behavior. Questions remain about how it ate, how it moved, its possible running speed, and its overall physiology. Its scientific classification is also debated. For example, the Asian dinosaur Tarbosaurus bataar is extremely similar to Tyrannosaurus, and is sometimes considered part of the same genus. Some North American tyrannosaurids have been combined with Tyrannosaurus, while certain Tyrannosaurus fossils have been suggested as representing separate species. The legitimacy of these species, including the recently described Tyrannosaurus macraensis, is still disputed among scientists. Since the early 20th century, Tyrannosaurus has been one of the most famous and recognized dinosaurs in the world. Science writer Riley Black has called it the ultimate dinosaur. Its fossils are highlights in museums worldwide and have captured the public imagination through appearances in books, movies, and media, most famously in the Jurassic Park franchise. Tyrannosaurus rex continues to stand as a symbol of prehistoric power, mystery, and fascination, embodying the grandeur of a world that existed tens of millions of years before humans ever walked the earth. The story of Tyrannosaurus rex, one of the most iconic and awe-inspiring dinosaurs to have ever walked the earth, begins not with a grand discovery, but with a small, solitary tooth. In the heat of July of 1874, high upon South Table Mountain, near the bustling town of Golden, in what is today the state of Colorado, a young student named Peter T. Dotson, under the guidance of Professor Arthur Lakes, unearthed a single fossilized tooth. At the time, the significance of this tiny remnant was not fully understood, but it would later become one of the earliest pieces of evidence that would eventually be attributed to the great Tyrannosaurus rex. The find marked a humble yet pivotal beginning to the long and fascinating story of the discovery and scientific study of this giant predator. A few decades later, in the early 1990s, the western plains of the United States continued to reveal their prehistoric secrets. John Bell Hatcher, a skilled fossil collector working in eastern Wyoming, gathered a number of postcranial bones, meaning parts of the skeleton other than the skull. Initially, these fossils were thought to belong to a large species called Ornithomimus grandis, a dinosaur that was then believed to resemble the modern ostrich in body form. Today, we understand that these bones were actually from Tyrannosaurus rex, further highlighting how difficult it was for early paleontologists to correctly classify fossils without the benefit of extensive comparative collections or modern technology. In 1892, the celebrated paleontologist Edward Drinker Cope discovered two fragmented vertebrae belonging to a massive dinosaur. Cope, who was no stranger to rivalry and rapid publication in the field of paleontology, believed these vertebral pieces belonged to a ceratopsid dinosaur, a group of horned dinosaurs including the famous Triceratops. He gave the new species the name Manospondylus gigas, which can be translated from Latin as giant porous vertebra, a reference to the many tiny holes in the bones that had likely served as channels for blood vessels. For more than a decade, these remains were misinterpreted. It was not until 1907 that John Bell Hatcher re-examined the fragments and realized that they did not belong to a horned dinosaur at all, but rather to a theropod, a group of bipedal carnivorous dinosaurs to which Tyrannosaurus rex belongs. By 1917, Henry Fairfield Osborn, the influential president of the American Museum of Natural History, noted the striking similarity between Manospondylus gigas and what would become recognized as Tyrannosaurus rex. Unfortunately, by that time, the second vertebra of the Manospondylus specimen had been lost, leaving only a single fragment. Because the material was so incomplete, Osborn refrained from officially merging the two names, instead treating the older genus, Manospondylus, as indeterminate. However, the connection between these early finds hinted at a broader and more fascinating story waiting to be pieced together. More than 80 years later, in June of 2000, the Black Hills Institute, a private paleontology organization known for fieldwork in the American West, discovered roughly 10% of a Tyrannosaurus skeleton, catalogued as BHI 6248, at a location that might well have been the original site where the Manospondylus gigas fossils had been unearthed. The first substantial and widely recognized Tyrannosaurus rex fossils were discovered in the early years of the 20th century by Barnum Brown, a pioneering paleontologist and assistant curator at the American Museum of Natural History. In 1900, Brown found a partial skeleton in eastern Wyoming, marking the first significant breakthrough in the hunt for this legendary predator. 2 years later, in 1902, he uncovered another partial skeleton in the famous Hell Creek Formation of Montana. This discovery included approximately 34 fossilized bones, providing an unprecedented glimpse into the anatomy of the creature. Writing about the find at the time, Brown marveled, "Quarry number 1 contains the femur, pubes, humerus, 3 vertebrae, and 2 undetermined bones of a large carnivorous dinosaur not described by Marsh. I have never seen anything like it from the Cretaceous." His excitement and astonishment reflected the rarity and magnitude of the find, as well as the sense of wonder that surrounded dinosaurs during that era. Henry Fairfield Osborn formally named the second skeleton Tyrannosaurus rex in 1905, creating one of the most famous binomials in the history of paleontology. The name Tyrannosaurus derives from the Greek words tyrannos, meaning tyrant, and sauros, meaning lizard, while the species name, rex, comes from Latin meaning king. Thus, Tyrannosaurus rex translates to tyrant lizard king, a title that conveys both the enormous size of the animal and its presumed dominance over other creatures in its ecosystem. That same year, Osborn also gave a name to the other specimen, calling it Dinosaurus imperiosus. It was not until 1906 that Osborn realized both skeletons belonged to the same species and decided to retain the name Tyrannosaurus as the preferred designation. The fate of these early specimens illustrates the complex history of museum collections and scientific discovery. In 1941, the type specimen of Tyrannosaurus rex was sold to the Carnegie Museum of Natural History in Pittsburgh, Pennsylvania, for the sum of $7,000, a considerable amount for the time. The original Dinosaurus material, meanwhile, found a permanent home in the collections of the Natural History Museum in London. Though Dinosaurus was ultimately recognized as synonymous with Tyrannosaurus, the name would later be honored in 2018 when paleontologist Andrew MacDonald and colleagues described a new species of tyrannosaurid Dinomaterra dynasties. The choice of name was a nod to Dinosaurus, a childhood favorite of MacDonald's, reflecting the enduring influence of early discoveries on modern paleontology. For several decades, the legacy of Barnum Brown's discoveries remained unchallenged. From the 1910s through the end of the 1950s, his specimens constituted the entirety of known Tyrannosaurus material. The Great Depression, followed by the outbreak of World War II, kept many paleontologists away from the field, and fossil exploration slowed dramatically. Nevertheless, interest in Tyrannosaurus would reignite in the decades that followed, leading to a remarkable expansion of our knowledge of the species. Beginning in the 1960s, paleontologists renewed their efforts in the fossil-rich badlands and plains of western North America, recovering an impressive 42 Tyrannosaurus skeletons. These specimens varied widely in completeness, ranging from 5 to 80% of the skeleton by bone count, offering paleontologists new opportunities to reconstruct the anatomy and behavior of the animal. In 1967, Dr. William McManus located and excavated a skeleton. Though this specimen was only about 15% complete by bone count, a reconstructed skull was displayed at the Museum of the Rockies, providing an invaluable educational resource for visitors and researchers alike. The 1990s marked a particularly fruitful period in Tyrannosaurus research, with discoveries outpacing all previous decades combined. Two of the most complete skeletons ever found, known as Sue and Stan, were recovered during this time. Sue, discovered by amateur paleontologist Sue Hendrickson on August 12, 1990, in the Hell Creek Formation, remains the most complete Tyrannosaurus skeleton ever uncovered, with approximately 85% of the bones preserved. The discovery of Sue set off a dramatic legal battle over ownership, which was eventually settled in 1997 in favour of Maurice Williams, the original landowner. The fossil was then purchased by the Field Museum of Natural History in Chicago at auction for a staggering $7,600,000, making it the most expensive dinosaur skeleton at that time. This record would be surpassed in 2020, when the skeleton known as Stan sold for $31,800,000. Once acquired by the Field Museum, Sue's bones required an immense amount of preparation. From 1998 to 1999, museum staff spent more than 25,000 hours carefully removing rock from the fossilized bones. After this painstaking work, the bones were sent to New Jersey, where the mount was constructed before being shipped back to Chicago for final assembly. The mounted skeleton was unveiled to the public on May 17, 2000, allowing millions of visitors to experience the majesty of Tyrannosaurus rex up close. Scientific studies of Sue's fossilized bones revealed fascinating details about her life. Researchers determined that she reached full size at the age of 19 and lived until she was 28 years old, making her the longest-lived Tyrannosaurus known to science. In the fascinating and ever-unfolding story of Tyrannosaurus rex discoveries, one of the most remarkable specimens is a skeleton affectionately nicknamed Stan. Stan, catalogued as BHI 3033, was named in honour of the dedicated amateur paleontologist Stan Sakrason. The fossil was unearthed in the year 1992 from the famous Hell Creek Formation, a rich fossil-bearing region that spans parts of Montana, North Dakota, South Dakota and Wyoming, known for preserving some of the last creatures to roam the Earth during the late Cretaceous period. Stan is an exceptional find, standing as the second most complete Tyrannosaurus skeleton ever recovered. Paleontologists painstakingly retrieved 199 bones, which together account for approximately 70% of the animal's total skeleton. 6 years later, in the year 1998, a young and keenly observant 20-year-old named Bucky Derflinger made a discovery that would mark him as the youngest person ever to find a Tyrannosaurus fossil. While exploring, he noticed what appeared to be a toe bone exposed above the ground. The specimen he had found was subsequently named Bucky, in recognition of his role in bringing it to light. Unlike some of the more massive adult specimens, Bucky represented a young adult Tyrannosaurus, standing approximately 3 meters tall, which is about 10 feet, and stretching nearly 11 meters in length, which converts to roughly 35 feet from snout to tail. This discovery was particularly important because it provided paleontologists with the first known Tyrannosaurus fossil that preserved a furcula, commonly known as the wishbone, a feature previously undocumented in this species. Bucky's fossil now resides permanently on display at the Children's Museum of Indianapolis, inspiring countless young visitors with the tangible presence of one of history's most formidable predators. The preservation of such delicate elements as the furcula allows scientists to better understand the skeletal anatomy and the evolutionary links between dinosaurs and modern birds, offering clues to how these magnificent creatures held their massive frames together and moved with astonishing power and grace. The turn of the new millennium brought with it further remarkable finds. During the summer of the year 2000, a field crew led by the renowned paleontologist Jack Horner embarked on an expedition near the Fort Peck Reservoir, a sprawling water body created by the damming of the Missouri River in northeastern Montana. This team discovered 5 new Tyrannosaurus skeletons, adding valuable specimens to the growing collection of known fossils and offering new opportunities to study the lives of these ancient predators. Just 1 year later, in 2001, another significant discovery was made in the Hell Creek Formation by a team from the Burpee Museum of Natural History. They unearthed a skeleton that was approximately 50% complete, belonging to what initially appeared to be a small, pygmy tyrannosaurid. This specimen was affectionately named Jane, catalogued as BMRP 2002.4.1. Jane's discovery ignited considerable excitement and debate within the paleontological community, as early interpretations suggested she might belong to a separate genus, Nanotyrannus, characterized by smaller adult size. However, further research and careful analysis ultimately indicated that Jane was more likely a juvenile Tyrannosaurus. This conclusion made Jane the most complete juvenile Tyrannosaurus specimen ever discovered, offering an unprecedented window into the growth stages and development of one of the largest land predators to have ever existed. Jane is currently on display at the Burpee Museum of Natural History, where visitors can marvel at the sight of a young Tyrannosaurus and imagine it roaming the subtropical landscapes of North America nearly 66 million years ago. In the year 2002, amateur fossil collectors Dan Wells and Don Wirrick discovered another intriguing Tyrannosaurus specimen. This fossil, later nicknamed Wyrex, consisted of 114 bones, which represented approximately 38% of the total skeleton. The excavation of Wyrex became a landmark event, not only for its paleontological significance, but also because it was completed over a 3-week period in the year 2004 by the Black Hills Institute. In the year 2006, researchers at Montana State University announced a discovery that would redefine our understanding of Tyrannosaurus anatomy. The university had obtained the largest Tyrannosaurus skull ever documented, belonging to a specimen catalogued as MR008. This colossal skull measured approximately 5 feet in length, or 152 centimeters, dwarfing previous finds and emphasizing the tremendous size these predators could reach. Subsequent comparisons with other notable specimens revealed fascinating distinctions. While MR008 held the record for overall size, the longest Tyrannosaurus skull belonged to a specimen catalogued as LACM 23844, measuring 136.5 centimeters, which is roughly 53.7 inches. Meanwhile, the widest Tyrannosaurus skull ever documented was that of the famous Sioux, measuring 90.2 centimeters, or approximately 35.5 inches across. These discoveries provided crucial data for understanding the biomechanics, feeding behavior, and evolutionary adaptations of Tyrannosaurus, highlighting how size and structure varied among individual members of the species. Footprints of Tyrannosaurus also provide a unique lens into its behavior and movement. 2 isolated fossilized footprints have been tentatively attributed to T-Rex. The first of these was discovered in the year 1983 at Philmont Scout Ranch in New Mexico by the American geologist Charles Pillmore. Initially, the footprint was thought to belong to a hadrosaurid, a group of herbivorous dinosaurs, due to its size and shape. However, upon closer examination, paleontologists noted the presence of a large heel, a feature unknown in tracks made by ornithopod dinosaurs, as well as traces of what may have been a hallux, or dewclaw-like 4th digit, characteristic of the Tyrannosaurus foot. This footprint was formally described and published in the year 1994 by Martin Lockley and Adrian Hunt, who named it Tyrannosaurus pillmoreae in honor of its discoverer. The track measures 83 centimeters in length, or 33 inches, and 71 centimeters in width, or 28 inches. It was formed in what was once a vegetated wetland mudflat, providing a rare snapshot of a Tyrannosaurus stepping through its environment tens of millions of years ago. A second footprint, also believed to have been made by a Tyrannosaurus, was first reported in the year 2007 by the British paleontologist Phil Manning. This track was found in the Hell Creek Formation of Montana and measured 72 centimeters, or 28 inches, in length, slightly shorter than the Philmont footprint. While there remains some uncertainty about whether this track definitively belonged to a Tyrannosaurus, the species remains the only known large theropod present in the Hell Creek Formation during the late Cretaceous, making it the most likely candidate. These fossilized footprints are invaluable for paleontologists because they provide direct evidence of how Tyrannosaurus moved, how its feet interacted with the terrain, and how speed and stride varied among individuals of different sizes. In the year 2016, a set of footprints from Glen Rock, Wyoming, dating to the Maastrichtian stage of the late Cretaceous and originating from the Lance Formation, were described by researchers Scott Persons, Phil Curry, and their colleagues. These tracks are believed to belong to either a juvenile Tyrannosaurus rex or to the more controversial and debated tyrannosaurid Nanotyrannus lancensis. By carefully measuring the size and spacing of the footprints and analysing the pattern in which they were made, researchers were able to estimate that the animal was moving at a walking speed of approximately 2.8 to 5 miles per hour. Additionally, based on the size of the footprints, the hip height of the dinosaur was calculated to range between 1.56 and 2.06 meters, or approximately 5.1 to 6.8 feet. A follow-up study published the following year in 2017 suggested that these estimates of speed could be increased by 50 to 80%, indicating that even juvenile or smaller Tyrannosaurus individuals were capable of moving with surprising agility and efficiency. Taken together, these discoveries, from the almost complete skeleton of Stan, with his healed injuries and scarred bones, to the young adult Bucky with his preserved wishbone, to the juvenile Jane providing insights into growth patterns, to the Wyrex excavation that captured public imagination, to the enormous skulls of MR008, LACM 23844, and Sioux, and finally to the rare fossilized footprints that hint at speed, gait, and behavior, paint a vivid and intricate picture of Tyrannosaurus rex. Each fossil adds a new chapter to the story of this iconic predator, deepening our understanding of its anatomy, behavior, and evolution, while also capturing the imagination of scientists, students, and dinosaur enthusiasts around the world. The continuous unearthing of specimens, careful study of skeletal injuries and growth patterns, innovative live documentation of excavations, and the discovery of fossilized footprints together reveal a dynamic and fascinating portrait of a creature that ruled the ecosystems of late Cretaceous North America with unmatched power and presence. One of the most famous and complete T-Rex skeletons ever discovered is Sue, which now resides at the Field Museum of Natural History in Chicago. Sue is a remarkable example of Tyrannosaurus anatomy, measuring approximately 12 meters and 30 centimeters to 12 meters and 40 centimeters in length, which is around 40 to 41 feet. At the hips, Sue stood about 3 meters and 66 centimeters to 3 meters and 96 centimeters tall, roughly 12 to 13 feet. The most recent scientific studies, which have applied a range of techniques to understand her weight, suggest that Sue's body mass reached around 8 metric tons and 400 kilograms to 8 metric tons and 460 kilograms, equivalent to about 8 1/3 long tons or 9 1/4 short tons. These figures place Sue among the heaviest land predators ever known. Another truly impressive specimen is known as Scotty, housed at the Royal Saskatchewan Museum. Scotty is slightly longer than Sue, measuring approximately 13 meters or 43 feet from snout to tail. Using a method that estimates mass based on the circumference of the femur, Scotty is considered the heaviest known Tyrannosaurus, with an estimated body mass of about 8 metric tons and 870 kilograms, equivalent to roughly 8 3/4 long tons or nearly 9 3/4 short tons. These two specimens alone illustrate the incredible variation in size among T-Rex individuals and the sheer power they must have possessed. Despite these record-breaking giants, not every adult Tyrannosaurus reached such monumental proportions. Over the years, scientists' estimates of the average adult mass have varied widely. In some earlier studies, estimates suggested adults might weigh as little as 4 metric tons and 500 kilograms, about 4.5 long tons or 5 short tons. Later research raised the possible upper range to more than 7 metric tons and 200 kilograms, roughly 7 1/10 long tons or nearly 8 short tons. Today, the most widely accepted range for an average adult T-Rex lies between 5 metric tons and 400 kilograms to 8 metric tons, which is about 5 1/3 to 7 9/10 long tons or 6 to 8 8/10 short tons. Interestingly, a study published in 2024 found little evidence that males and females differed significantly in size, suggesting that sexual dimorphism, the difference in size between sexes, was minimal in this species. The skull of Tyrannosaurus was another marvel of evolution. The largest known skulls reach up to 1 meter and 54 centimeters, approximately 5 feet and 1 inch in length. Like all large carnivorous theropods, the skull contained large fenestraux, or openings, which helped to reduce its overall weight without compromising strength. However, Tyrannosaurus's skull was unique compared to other large meat-eating dinosaurs outside its family. Its back portion was extremely wide, while the snout remained narrow, a combination that allowed for unusually precise binocular vision, giving it an advantage when hunting. The skull bones were massive, and several, including the nasals, were fused together, preventing movement between them and adding strength. Many of the bones were also pneumatized, meaning they contained a honeycomb of air pockets, which made them lighter without losing durability. These features contributed to an exceptionally strong bite, far more powerful than that of any non-tyrannosaurid predator. The tip of the upper jaw was U-shaped, a contrast to the V-shaped jaws of most other carnivores, allowing Tyrannosaurus to grasp and tear large chunks of flesh and bone in a single bite, though it placed additional stress on the front teeth. Tyrannosaurus teeth were equally remarkable, showing clear differences in shape, a condition known as heterodonty. The 4 teeth at the front of each side of the upper jaw were closely packed and D-shaped in cross-section, with small reinforcing ridges on the rear. Their tips were chisel-like and curved backward, reducing the risk of breaking during a powerful bite and pull. The remaining teeth, which were more widely spaced and shaped like thick curved bananas rather than straight daggers, were reinforced to handle the enormous forces of biting. Mature T-Rex individuals had 12 of these larger teeth on each side of the upper jaw, generally bigger than those in the lower jaw except near the back. The largest known tooth is estimated to have been about 30 centimeters, or 12 inches, long when it was alive, including the root, making it the largest tooth of any carnivorous dinosaur discovered so far. The lower jaw was equally strong, bearing 13 teeth in the front dentary bone, with the back portion of the jaw becoming significantly taller. Both jaws contained numerous small holes called foramina, whose purposes are still studied today. Some researchers believe they could have housed a sensory system similar to crocodiles, while others suggest they might indicate the presence of lips or scales around the mouth, a theory supported by studies of tooth-wear patterns. The vertebral column of Tyrannosaurus was a complex and fascinating structure. It included 10 neck vertebrae, 13 back vertebrae, and 5 sacral vertebrae fused to the pelvis. The tail likely contained at least 40 vertebrae, though the exact number may have varied among individuals. For example, Sue was mounted with 47 tail vertebrae. The neck formed a natural S-shaped curve, but it was notably short, deep, and muscular compared to other theropods, designed to support the massive skull. The second vertebra, called the axis, was especially short, while the remaining neck vertebrae were weakly opisthocoelous, meaning the front of each vertebral body was convex and the back concave. Each vertebra contained a single pluricoel, a depression caused by air sacs, which lightened the skeleton. The torso vertebrae were robust but had a narrow waist, with keels on their undersides and deep concave troughs on the front sides. They also contained large pluricoels, and the neural spines were roughened to anchor strong tendons. The sacral vertebrae were fused and pneumatized, linking the spine firmly to the pelvis via transverse processes and sacral ribs. The tail was long, heavy, and moderately stiff, designed to balance the massive head and torso while providing space for enormous locomotor muscles attached to the thighs. The 13th tail vertebra marked the transition from the deep tail base to the more flexible middle tail, which was stabilized by long articulation processes. Underneath the trunk, Tyrannosaurus had 18 or 19 pairs of segmented belly ribs, adding further support to the massive body. The shoulder area of this mighty predator was astonishingly long, even longer than the entire length of its short forelimbs. The shoulder blade itself was shaped with a narrow shaft that suddenly expanded into a broad, impressive upper end. From this upper section, a long forward-pointing projection connected it to the coracoid, which had a rounded, solid appearance. Both shoulder blades were joined together by a small furcula, resembling a delicate wishbone. Beneath the chest, the paired breastbones were likely made of cartilage alone, rather than solid bone, suggesting a lighter, more flexible structure. The arms of this creature were extremely short when compared to its massive body. The upper arm bone, or humerus, was compact but robust, ending in a very rounded head despite its narrow upper part. The two bones of the lower arm, the ulna and radius, were straight and notably shorter than the humerus, giving the forelimb a stubby appearance. Interestingly, the second metacarpal, the bone in the hand, was longer and wider than the first metacarpal, which is unusual, as in most theropods the first metacarpal is the dominant one. The hands bore only 2 clawed fingers, though a tiny splint-like third metacarpal remained, hinting at a vestigial third finger that had almost vanished over evolutionary time. The pelvis of this predator was massive and highly developed. The uppermost bone, the ilium, was both very long and towering in height, providing a large surface for the attachment of powerful hind limb muscles. The front bone of the pelvis, the pubis, ended in an enormous boot-shaped extension far longer than the shaft itself. The rear bone, the ischium, was slender, straight, and angled backward and downward, creating a structure that supported the immense hindquarters. In stark contrast to the tiny arms, the hind limbs were incredibly long in proportion to the animal's body, rivaling the length of legs in any theropod ever known. In the foot, the 3 main metatarsals formed what paleontologists call an arctometatarsallian structure, where the middle of the third metatarsal near the ankle was pinched between the surrounding bones. This third metatarsal also had a remarkable winding curve. To support such a giant body without becoming unbearably heavy, many bones throughout the skeleton were hollowed, reducing weight while retaining strength. Tyrannosaurus stands as the defining genus for its entire group. It is the reference point for the superfamily Tyrannosauridae, the family Tyrannosauridae, and the subfamily Tyrannosaurini. In other words, when paleontologists find a new species, they compare it to Tyrannosaurus to decide if it belongs in the same family. Other members of the Tyrannosaurid subfamily include the North American Daspletosaurus and the Asian Tarbosaurus. In some cases, these species have even been suggested to be the same as Tyrannosaurus. For many years, scientists thought that Tyrannosaurids descended from earlier, giant theropods like megalosaurs and carnosaurs. However, more recent research has placed them closer to generally smaller, faster theropods known as coelurosaurs. The earliest members of this group were crested Proceratosaurids, while later, more advanced tyrannosaur species are classified under the Pantyrannosauria. These creatures started out relatively small, but by the early Cretaceous period some had grown to massive sizes. It seems likely that tyrannosauroids became dominant after other giant theropods, like allosauroids and megalosauroids, began to decline during the early stages of the late Cretaceous. Tyrannosauroids can be identified by their fused nasal bones and distinctive teeth. Pantyrannosaurs, a subgroup, had unique hip features, a large opening in the quadrate bone, wide bones behind the eyes, and hourglass-shaped nasal bones. Some more advanced Pantyrannosaurs began losing air-filled cavities in their nasal bones, reducing the size of their upper arms relative to their thighs, and slowly shrinking their forelimbs. They also started developing an arctometatarsalia foot, similar to Tyrannosaurus. In Eutyrannosaurs, the nasal bones were rough-textured, and the lower jaw had a smaller external opening. True Tyrannosaurids lacked flexible skull joints or special crests on the nose, but had distinctive features on the lacrimal bones near the eyes and a narrow strut between openings in the upper jaw. Many evolutionary studies have found that Tarbosaurus bataar, a giant Asian tyrannosaur, is the closest relative or sister species of Tyrannosaurus rex. The discovery of the Tyrannosaurid Lithranax further supports this, suggesting that Tyrannosaurus, Tarbosaurus and the Asian Juchengtyrannus formed a closely related group, with Lithranax as a sister taxon. A study in 2016 by Steve Brusata, Thomas Carr and colleagues also proposed that Tyrannosaurus may have originated in Asia, possibly descending from Tarbosaurus. In 2024, Dalman and colleagues described a new species, Tyrannosaurus macraensis, and found results consistent with earlier studies. They confirmed that Tyrannosaurus is closely related to the clade formed by Tarbosaurus and Juchengtyrannus, known as the Tyrannosaurini. They also provided support for a separate monophyletic group containing Daspletosaurus and Thanatothyristes, which is generally called the Daspletosaurinae. In the year 1955, the Soviet paleontologist Evgeny Maleev made a remarkable announcement that would add a new name to the ever-growing list of giant prehistoric predators. He described a species of tyrannosaur discovered in the vast expanses of Mongolia and gave it the name Tyrannosaurus bataar. This initial classification suggested that the Mongolian tyrannosaur was closely related to the famous Tyrannosaurus rex of North America. A decade later, in 1965, further studies led scientists to reclassify this species, recognizing it as belonging to its own distinct genus. Hence, it became known as Tarbosaurus bataar. Despite this reclassification, the scientific community has remained divided. Many paleontologists continue to treat Tyrannosaurus and Tarbosaurus as separate genera, but a handful of researchers, including Thomas Holtz, Kenneth Carpenter, and Thomas Carr, have argued that the two are so similar that they might actually belong to the same genus, potentially restoring the original name for the Mongolian species. Meanwhile, in the late 20th century, several tyrannosaur fossils uncovered in China were initially assigned as new species of Tyrannosaurus. In 1975, a single lateral tooth found in the red beds of Yunnan province was described as Tyrannosaurus lanpingensis. A few years later, in 1978, a specimen from the Subashi Formation in the Turpan Basin, Xinjiang, was named Tyrannosaurus turpanensis. Shortly afterward, between 1979 and 1980, fossils from the Quiba Formation in the Tantu Basin of Henan province led to the description of Tyrannosaurus luanchuanensis. However, these Chinese taxa were all published with minimal description, leaving their scientific standing unclear. By 2004, Thomas Holtz reviewed these fossils and concluded that all of them were best understood as junior synonyms of Tarbosaurus bataar, meaning they did not represent separate species after all. Elsewhere, in Russia, a large phalanx bone catalogued as VGI number 231/3 was initially assigned to Tyrannosaurus by Yarkov in the year 2000. It had been discovered in the lower Maastrichtian deposits at Bereslavka. Later, in 2004, scientists Averyanov and Yarkov re-examined the fossil and concluded that it was more likely a metacarpal or metatarsal bone, possibly belonging to a ceratosaur rather than a tyrannosaur. In their comprehensive review of 2023, Averyanov and Lopatin mentioned this specimen, as well as a single tooth from the same locality, only as indeterminate theropods. In China, the early 21st century saw similar complexities. In 2001, paleontologist Hu Chengji described several tyrannosaurid teeth and a metatarsal found in a quarry near Jucheng as a new species, Tyrannosaurus juchengensis. A decade later, in 2011, a right maxilla and a left jawbone from a nearby site were assigned to a new tyrannosaurid genus, Juchentyrannus. Some scientists now suspect that T. juchengensis may actually represent the same species as Juchentyrannus. Regardless, because the original holotype of T. juchengensis lacks the unique features needed to distinguish it clearly from other tyrannosaurians, it is generally considered a nomen dubium, or a dubious name. In North America, discoveries also added layers of complexity. In 2006, a fragmentary lacrimal bone, CM9401, from the Judith River Formation in Fergus County, Montana, was described as potentially belonging to Tyrannosaurus. This right lacrimal had originally been collected alongside the type specimen of Deinosuchus rugosus, a giant prehistoric crocodile, and remained undescribed until the 1980s, when paleontologist Dale Russell identified it as part of a tyrannosaurid skull. The bone closely resembles the lacrimals of Tyrannosaurus rex in both size and shape. Unlike earlier tyrannosaurids, such as Albertosaurus and Gorgosaurus, which typically have a pronounced lacrimal horn, this specimen displays a roughened dorsal surface, a feature consistent with T-Rex and its Asian cousin, Tarbosaurus. The impressive size of CM9401 suggests it belonged to a large tyrannosaurid, dating from the Campanian stage around 75 million years ago, which is notably earlier than the usual Maastrichtian age range of 68 to 66 million years for T-Rex. However, the precise age and origin of CM9401 remain uncertain due to incomplete field records. Further studies continue to challenge conventional ideas. In 2018, researchers studying tyrannosaurid teeth from the Two Medicine Formation noted that a premaxillary tooth bore a strong resemblance to the teeth of the famous Sioux specimen of T-Rex, to the exclusion of any other Campanian tyrannosaurid. They also suggested that the Montana lacrimal may have originated from the same formation, citing similarities in preservation between its locality and the Willow Creek anticline where the tooth was found. If accurate, this would place both fossils in the Flag Butte member of the Two Medicine Formation, dating from approximately 77 to 76.3 million years ago. This would make them far older than any other known T-Rex specimens and contemporaneous with Daspletosaurus. In 2025, paleontologist Charlie Shearer used these findings to argue that the Tyrannosaurini group may not have evolved directly from Daspletosaurus, challenging previous evolutionary assumptions. In 2022, Gregoris Paul and his colleagues proposed a radical reinterpretation of Tyrannosaurus rex. They suggested that what had long been considered a single species was actually three distinct species. The first retained the familiar name Tyrannosaurus rex, the second was named Tyrannosaurus imperator, meaning tyrant lizard emperor, and the third was called Tyrannosaurus regina, meaning tyrant lizard queen. The holotype of T. imperator is the Sioux specimen, while the holotype of T. regina is the Wankel specimen. This classification was based largely on differences in the robustness and proportions of the femur and other bones across specimens, as well as variation in the number of small front teeth in the lower jaw. According to their analysis, T-Rex exhibits robust skeletal anatomy with a moderate femur length to circumference ratio and a single slender incisiform tooth in the dentary. T. imperator is also robust, but has a lower femur ratio and two slender incisiform teeth, while T. regina is more gracile, with a higher femur ratio and one slender tooth. Despite this detailed proposal, many leading paleontologists expressed skepticism. Experts including Stephen Brusate, Thomas Carr, Thomas Holtz, David Hone, Jingmai O'Connor and Lindsay Zano questioned the study's conclusions. Holtz and Zano noted that more than one species of Tyrannosaurus might exist but felt the evidence was insufficient to support the specific species proposed. Holtz also pointed out that if T. imperator were valid, it might be the same as Nanotyrannus lancensis, in which case it should be called Tyrannosaurus lancensis. O'Connor, curator at the Field Museum where Sue is displayed, considered the new species poorly supported and not sufficient to warrant changes to the exhibit labels. Brusate, Carr and O'Connor suggested that the differences noted among specimens likely reflect natural variation within a single species. Both Carr and O'Connor also raised concerns that the study could not reliably assign several well-preserved specimens to the proposed species. Additionally, Philip J. Curry, who originally co-authored the study, withdrew from it to avoid participating in the naming of the new species. In a paper published in the year 2025, the paleontologist Paul continued to argue that the species Tyrannosaurus imperator and Tyrannosaurus regina were valid and distinct. He claimed that these proposed species could be told apart by the shape of the bony ridges behind their eyes, known as postorbital bosses, which were subtle but important differences in skull anatomy. The previous year, in 2024, a team led by Dalman described the remains of a tyrannosaur that had originally been discovered much earlier, in the year 1983, in the Hall Lake Formation of New Mexico, which dates to the Campanian to early Maastrichtian stage of the late Cretaceous. These fossil bones are now kept at the New Mexico Museum of Natural History and Science. The material includes parts of the skull such as the right postorbital, right squamosal, left palatine, and a partially preserved maxilla. From the lower jaw, the fossils include the left dentary, right splenial, right prearticular, right angular, and right articular bones, as well as some isolated teeth and chevrons, the bones from the tail. Some of these bones were briefly mentioned in 1984 as belonging to Tyrannosaurus rex, and a more detailed description appeared in 1986. In 1990, Lehman and Carpenter suggested that this specimen might represent a new genus of tyrannosaur, a claim which Carr and Williamson later disputed in the year 2000. By the year 2015, Sullivan and Lucas argued that there was little evidence to confidently identify as Tyrannosaurus rex, and they tentatively labelled it as CF. Tyrannosaurus sp, meaning it probably belonged to the genus but was uncertain at the species level. They also suggested that this McRae tyrannosaur likely lived before the Lanchian Age, which was before 67 million years ago, based on its probable association with fossils of the giant dinosaur Alamosaurus. In 2024, Dalman and colleagues proposed a new species name, Tyrannosaurus macraensis, for the holotype referencing the McRae group, the geological formation that includes the Hall Lake Formation. This specimen comes from rock layers that are a few million years older than the time when Tyrannosaurus rex is thought to have lived, at the very end of the Maastrichtian stage. The initial dating of these layers placed them between 72.7 and 70.9 million years ago, corresponding to the latest part of the Campanian or the very earliest Maastrichtian. However, in a conference abstract later that same year, researchers estimated that the specific layer containing T. macraensis was younger than 69 million years, plus or minus 0.4 of a million years, and older than 66 million years, based on sandstone in the same area. This suggests that T. macraensis may have lived closer in time to T-Rex than originally thought. Tyrannosaurus macraensis is estimated to have been around 12 meters long, approximately 39 feet, making it a similar size to an adult T-Rex. However, the two can be distinguished by features of the skull. The lower jaw of T. macraensis is proportionally longer, has a less prominent chin, and is shallower than that of T-Rex, indicating a somewhat weaker bite. Its teeth are blunter and more flattened from side to side, and the ridges behind its eyes are less pronounced. Other parts of its skeleton show similarities to the tyrannosaurs Tarbosaurus and Juvenile. Despite this, the validity of T. macraensis was questioned by other researchers in 2025. Morrison and colleagues pointed out uncertainties in the previous age estimates. They argued that using the Alamosaurus fossil as a marker to date the Hall Lake Formation was unreliable, because the sedimentation rates for that species vary widely. They also suggested that the skeletal features of the holotype might not fall outside the known variations seen in T-Rex. Regardless of whether T. macraensis was a distinct species or not, these researchers concluded that the genus Tyrannosaurus likely originated in western North America, in the landmass called Laramidia, and that its ancestors may have migrated from Asia. Later that same year, Voris and colleagues considered T. macraensis to be a junior synonym of T-Rex, agreeing that the stratigraphic data was problematic, and that all of the supposed unique features of T. macraensis were actually found within the normal variation of T-Rex. Similarly, Carr, in his study of the T-Rex holotype skull, did not recognize T. macraensis as a valid species, observing that the features proposed for the new species appeared throughout known T-Rex specimens. Other tyrannosaur fossils from formations containing T-Rex were initially named as separate species, including Orblicidon and Albertosaurus megagracilis, the latter being renamed Dinotyrannus megagracilis in 1995. These fossils are now universally considered to be juvenile T-Rex individuals. One possible exception is a small but nearly complete skull from Montana, measuring 60 centimeters, or 2 feet, long. This skull was first described as a species of Gorgosaurus called Gorgosaurus lancensis by Charles W. Gilmore in 1946. In 1988, paleontologists Robert T. Backer, Phil Curry, and Michael Williams, then curator of paleontology at the Cleveland Museum of Natural History, re-examined the skull, noting that the bones were fused, indicating it was an adult. They assigned it to a new genus, Nanotyrannus, meaning dwarf tyrant, because of its small size, estimating the dinosaur to have been around 5.2 meters long, or 17 feet. However, in 1999, Thomas Carr conducted a detailed analysis and concluded that the specimen was actually a juvenile, leading him and many others to classify it as a young T-Rex. In 2001, a more complete juvenile tyrannosaur nicknamed Jane was discovered. This specimen belonged to the same species as the original Nanotyrannus skull. The discovery of Jane prompted a focused conference on the validity of Nanotyrannus at the Burpee Museum of Natural History in 2005. Many paleontologists who had previously supported the idea of Nanotyrannus lancensis as a separate species, including Curry and Williams, concluded that the new juvenile evidence confirmed it was simply a young T-Rex. Despite this, Peter Larson continued to argue that Nanotyrannus might represent a separate, closely related species. He pointed to skull features, such as having 2 more teeth in each jaw than adult T-Rex, proportionally larger hands with an extra finger bone, and differences in the wishbone structure in an undescribed specimen. He also suggested that Stygivenator, generally thought to be a juvenile T-Rex, could in fact be an even younger Nanotyrannus. Later studies revealed that other tyrannosaurs like Gorgosaurus also showed a reduction in tooth count as they grew. Given the variation in tooth numbers within the same age group of Gorgosaurus and Tyrannosaurus, these differences are likely due to individual variation rather than representing separate species. By 2013, Carr noted that all of the differences once cited to support Nanotyrannus had been shown to result from growth, individual variation, or distortion of the bones, leaving no evidence that it was a separate species. In the year 2016, a detailed study by paleontologists Persons and Curry examined the proportions of the limbs in various tyrannosaur specimens. They suggested that the fossils attributed to Nanotyrannus might have shown different levels of running ability or cursoriality compared to Tyrannosaurus rex, hinting that Nanotyrannus could be a separate species. However, the renowned paleontologist Manabu Sakamoto cautioned that such a conclusion might be unreliable because it relied on a very small number of specimens. He pointed out that these differences in limb proportions did not necessarily indicate that Nanotyrannus was a distinct species at all. In that same year, another paleontologist, Joshua Schmerge, argued in favour of recognising Nanotyrannus as a valid species, focusing on features of the skull. In particular, he highlighted a dentary groove observed in the skull of specimen BMRP 2002.4.1. According to Schmerge, this groove was absent in Tyrannosaurus rex but present in the more distantly related Dryptosaurus and certain members of the Albertosaurans. This, he suggested, might mean that Nanotyrannus was a separate member of the Albertosaurinae, a subgroup of Tyrannosaurids. Yet, other researchers, including Carr and his colleagues in 2016, noted that this single feature was not enough to prove that Nanotyrannus was a distinct species. They pointed out that the dentary groove is quite common among tyrannosauroids and can change as the animals grew, making it an unreliable marker for classification. 4 years later, in the year 2020, Holly Woodward and her team carried out a careful study of all specimens that had been referred to Nanotyrannus. They found that every single one of these fossils belonged to young, not fully grown individuals. Their results suggested strongly that these fossils were likely juvenile Tyrannosaurus rex rather than a separate species. In the same year, Carr published a comprehensive paper on the growth and development of Tyrannosaurus rex. He examined specimen CMNH, 7,541, finding that it fell perfectly within the expected growth pattern for T-Rex. The specimen showed all the hallmarks of a juvenile, being less than 13 years old and having a skull less than 80 centimetres or roughly 31 inches in length. Among the 44 specimens he studied, Carr found no evidence of significant variation related to sex or evolutionary lineage. He observed that traits that might otherwise help distinguish different species tended to change gradually as the animal aged, tracking the overall growth of the dinosaur. Discussing his findings, Carr noted that the fossils attributed to Nanotyrannus actually represented a continuous growth sequence within Tyrannosaurus rex. They formed a natural bridge between the smallest juveniles and the subadult stages. If Nanotyrannus were truly a separate species, its specimens would have grouped distinctly apart from T-Rex, but that was not observed. Carr concluded that the nanomorphs are not all that similar to each other, and instead form an important bridge in the growth series of T. rex, capturing the beginnings of the profound change from the shallow skulls of juveniles to the deep, massive skulls seen in fully grown adults. Then, in the year 2024, researchers Nick Longrich and Evan Thomas Saiter re-examined the original Nanotyrannus fossils, including both the holotype and the other referred specimens. They considered multiple factors, including differences in anatomy, growth patterns, and evolutionary relationships. Based on their analysis, they suggested that Nanotyrannus might indeed represent a distinct species, possibly even falling outside the Tyrannosauridae family in some of their phylogenetic reconstructions. However, in the following year, 2025, Voris and colleagues critiqued this conclusion. They argued that the placement of Nanotyrannus in a more primitive evolutionary position by Longrich and Saiter could have been caused by characteristics associated with immaturity, as well as issues with the datasets used. Their work supported the earlier interpretation that Nanotyrannus fossils were more likely juveniles of Tyrannosaurus rex, rather than evidence of a separate species. The discovery and careful study of several juvenile Tyrannosaurus rex specimens have given scientists an extraordinary window into how these magnificent creatures grew, lived, and aged. By examining young individuals, researchers have been able to track the changes in body shape and size as T-Rex progressed from a small, nimble hatchling into a massive apex predator. They have also been able to estimate the typical lifespan of the species and understand how fast these giants gained their astonishing bulk. The smallest known Tyrannosaurus, catalogued as LACM 28470 and affectionately nicknamed the Jordan theropod, is estimated to have weighed a mere 30 kilograms, or about 66 pounds. At the opposite end of the spectrum stand some of the largest adults ever discovered, one of the most famous, the nearly complete skeleton called Sue, displayed at the Field Museum of Natural History in Chicago, likely weighed an astonishing 5,650 kilograms, roughly 12,460 pounds. Histological studies, which involve examining the microscopic structure of bones, have revealed that the tiny Jordan theropod was only about 2 years old when it died. Sue, on the other hand, was originally thought to have been 28 years old, which at the time was believed to be near the maximum lifespan of T-Rex. More recent research, however, suggests Sue could have been anywhere from 27 to 33 years old. Another famous specimen, Trix, catalogued as RGM 792,000, is estimated to have been at least 30 years old when it perished. These studies of bone structure, known as histology, have allowed paleontologists to determine the ages of many other T-Rex specimens as well. By plotting the ages and weights of different individuals on a graph, scientists can create a growth curve for the species. This curve has an S shape, illustrating the stages of growth over a T-Rex's life. Young dinosaurs stayed relatively small, usually under 1,800 kilograms or 4,000 pounds, until around 14 years of age. After this point, their growth accelerated dramatically. During this explosive growth phase, a young T-Rex could gain approximately 600 kilograms, or about 1,300 pounds, per year for the next 4 years. By the time a T-Rex reached 18 years old, the growth curve flattened again, showing that the rapid increase in size had slowed. For example, Sue, at 28 years old, weighed only about 600 kilograms more than a Canadian specimen aged 22, catalogued as RTMP 8112.1, Studies published in 2004 confirm that this rapid growth began to taper off around 16 years of age. In 2011, a study led by Hutchinson and colleagues reinforced the general findings of earlier research, but suggested an even more dramatic peak in growth. According to their calculations, the maximum growth rate during the exponential phase could reach 1,790 kilograms per year. While this was much higher than earlier estimates, it helped bridge the gap between observed growth rates and what would be expected for an animal of such immense size. Scientists believe that the sudden slowdown at the end of this growth spurt may mark physical maturity. Supporting this idea, a T-Rex from Montana, MOR 1125, nicknamed B-Rex, was found to contain medullary tissue in its femur, a type of tissue that, in modern birds, appears only in females during ovulation. Later, in 2016, Mary Higby Schweitzer, Lindsay Zano, and their team confirmed that the soft tissue in MOR 1125 was indeed medullary bone. Interestingly, other tyrannosaurids followed very similar growth patterns, though their maximum growth rates were lower, reflecting their smaller adult sizes. A study published in 2020 by Woodward and colleagues in the journal Science Advances revealed even more nuance in T-Rex development. They discovered that juvenile Tyrannosaurus could adjust their growth depending on environmental conditions such as food scarcity. By analysing 2 specimens between 13 and 15 years old from the Burpee Museum in Illinois, researchers found that these dinosaurs could slow their maturation rate when resources were limited. This remarkable flexibility would have made T-Rex particularly well suited to ecosystems where food availability shifted year by year, a condition that might have challenged smaller or less adaptable predators. The study also suggested that the dubious genus Nanotyrannus is actually synonymous with Tyrannosaurus, based on detailed analysis of bone growth rings. Mortality patterns in T-Rex were equally fascinating. Over half of all known specimens appear to have died within 6 years of reaching sexual maturity. This pattern mirrors what is observed in other tyrannosaurs and even in some modern large birds and mammals, which experience high infant mortality, followed by a period of relatively low mortality in juveniles, and then an increase again after reaching reproductive age. Some studies suggest that juvenile T-Rex fossils are rare because fewer young dinosaurs died during these years, reducing the chance they would be preserved. Additionally, the fossil record is incomplete, and collectors have historically favoured larger, more impressive specimens. Paleontologist Thomas Holtz Jr., in a lecture in 2013, famously remarked that dinosaurs lived fast and died young because they reproduced quickly, unlike mammals, which have longer lifespans due to slower reproductive rates. Similarly, Gregory Spall emphasized that Tyrannosaurus reproduced rapidly and died young, though he also pointed out that their lives were inherently dangerous. The question of whether Tyrannosaurus bore feathers has sparked intense debate. In 2004, filamentous structures, considered the precursors of feathers, were reported in the small, early Tyrannosauroid Dilong Paradoxus from the early Cretaceous Yixian Formation of China. Since the larger tyrannosaurids known at the time showed evidence of scales, researchers speculated that bigger species might have lost insulating feathers because of their smaller surface-to-volume ratio. This theory was challenged by the discovery of Eutyrannus huali, also from the Yixian Formation, a giant tyrannosauroid covered extensively in feathers, proving that even large tyrannosaurs could be feathered. In 2017, a comprehensive review of tyrannosaurid skin impressions, including those of a Tyrannosaurus specimen nicknamed Y-Rex, revealed patches of mosaic scales on the tail, hip, and neck. The study concluded that if feathers were present on large tyrannosaurids like Tyrannosaurus, they were probably restricted to the upper parts of the body. Through the combination of fossil evidence, bone histology, and meticulous research, scientists have been able to reconstruct an incredible story of T-Rex growth, reproduction, mortality, and even appearance. From the tiny 2-year-old Jordan theropod to the enormous, nearly 30-year-old Sioux, the life of a Tyrannosaurus emerges not merely as a tale of size and ferocity, but as a complex journey shaped by biology, environment, and the relentless march of time. As more and more Tyrannosaurus specimens were discovered, scientists began comparing differences between individual skeletons and noticed what seemed to be 2 distinct body types, or morphs, much like those seen in some other theropod species. One of these types appeared more heavily built and was called the robust morph, while the other, lighter and slimmer, was called the gracile morph. Many differences between these two types were once thought to reflect differences between males and females, with the robust form often suggested to be female. For instance, the pelvis of several robust specimens looked wider, possibly to allow eggs to pass through. It was also thought that robust individuals had a smaller chevron on the first tail vertebra, supposedly to make egg-laying easier, a claim originally made for crocodiles but later found to be incorrect. In recent years, evidence supporting sexual differences in T-Rex has weakened. A study in 2005 showed that earlier claims of sex-related differences in crocodile tail bones were mistaken, casting doubt on whether similar differences existed in T-Rex. Additionally, a full-size chevron was found on the first tail vertebra of Sioux, one of the most robust T-Rex specimens, showing that this feature could not reliably distinguish the two morphs. Differences between specimens found from Saskatchewan in Canada to New Mexico in the United States might instead reflect geographic variation or age, with more robust individuals being older animals. So far, only a single Tyrannosaurus specimen has been conclusively identified as female. Examination of B. rex revealed the presence of soft tissue preserved in several bones. Some of this tissue was identified as medullary tissue, a special tissue found in modern birds that stores calcium for eggshell formation during ovulation. Because only female birds naturally produce eggs, this tissue is normally found only in females, although males can make it if injected with female reproductive hormones like estrogen. This strongly suggests that B. rex was female and that she died while producing eggs. Recent studies have shown that crocodiles, thought to be the closest living relatives of dinosaurs, never produce medullary tissue, making its presence in birds and theropod dinosaurs additional proof of their close evolutionary connection. For much of the history of paleontology, Tyrannosaurus was imagined as a living tripod, standing with its body at a steep 45-degree angle or more upright, with the tail dragging along the ground, much like a kangaroo. This idea originated with Joseph Leidy's reconstruction of Hadrosaurus in 1865, the first dinosaur ever shown in a bipedal pose. In 1915, Henry Fairfield Osborn, the former president of the American Museum of Natural History, reinforced this view when unveiling the first complete T-Rex skeleton in an upright pose. This arrangement stood in the museum for 77 years, until it was dismantled in 1992. By 1970, scientists realized that such an upright posture could not have been maintained by a living animal, as it would have strained or dislocated multiple joints, including the hips and the connection between the head and spine. Nevertheless, the inaccurate upright mount influenced numerous films and artworks, including Rudolf Zallinger's famous mural, The Age of Reptiles, at Yale University's Peabody Museum, until the 1990s, when movies like Jurassic Park introduced a more realistic horizontal posture to the public. Today, T-Rex is depicted with its body nearly parallel to the ground, and its tail stretched behind to balance its massive head. When sitting, Tyrannosaurus may have leaned its weight backward onto a pubic boot, a wide expansion at the end of the pubis found in some dinosaurs, freeing the hind limbs for movement. Getting back up likely involved balancing the limbs under the body, with some help from the small forelimbs. This idea, known as Newman's push-up theory, has been debated. Still, it is likely that T-Rex could right itself if it fell, using the tail as a counterbalance. Evidence of healed stress fractures in the forelimbs has been interpreted in two ways. Either the arms were not very useful, or they were indeed used and occasionally injured like the rest of the body. When T-Rex was first discovered, only the humerus, the upper arm bone, was known. For the first public display in 1915, Osborn added longer, three-fingered forelimbs similar to those of Allosaurus. A year earlier, Lawrence Lamb had described the short, two-fingered forelimbs of the closely related Gorgosaurus, suggesting that T-Rex had similar forelimbs. This was confirmed in 1989 when the first complete T-Rex forelimbs were found with MR 555, nicknamed the Wankel Rex. The remains of Sioux also include complete forelimbs, T. Rex arms are very small for such a large animal, measuring only about 1 meter or 3 feet 3 inches long. Some early researchers considered them vestigial or useless. However, the bones show large areas for muscle attachment, indicating considerable strength. Osborn speculated as early as 1906 that the arms might have been used to hold a mate during copulation. In 1970, Newman suggested the arms helped T-Rex rise from a lying position. Other functions have been proposed, though some are seen as unlikely. In 2022, Padian argued that the small arms were a secondary adaptation. As tyrannosaurids evolved bigger, more powerful jaws and skulls, the arms became smaller to avoid injury from bites during feeding or fights. Another possibility is that the forelimbs helped hold struggling prey, while the massive jaws delivered the killing bite. Biomechanical studies support this idea. T-Rex forearm bones are extremely thick, suggesting they could withstand great force. The biceps alone could lift about 199 kilograms, or 439 pounds, and other muscles, such as the brachialis, worked with the biceps to make elbow flexion even stronger. The biceps of T-Rex were roughly 3.5 times stronger than those of a human. The forearms had a limited range of motion, with the shoulder and elbow able to move only about 40 and 45 degrees respectively. In comparison, the same joints in Deinosuchus could move 88 and 130 degrees, while human shoulders rotate 360 degrees and elbows move through 165 degrees. The strong bones, powerful muscles, and restricted motion suggest that the arms were designed to hold on to struggling prey. The first detailed study of Tyrannosaurus forelimbs by Kenneth Carpenter and Matt Smith rejected the idea that the arms were useless, or that T-Rex was solely a scavenger. Some researchers, like Stephen M. Stanley, suggested the arms were used as weapons to slash prey, using the claws to make deep cuts. However, Padian disagreed, arguing that Stanley had overestimated the size and motion of the arms. Tyrannosaurus, like most dinosaurs, was long thought to be cold-blooded, similar to modern reptiles. This view was challenged during the dinosaur renaissance starting in the late 1960s by scientists such as Robert T. Bakker and John Ostrom, who argued that T-Rex was warm-blooded and likely very active. Since then, paleontologists have studied its growth patterns and metabolism in detail. Histological studies show that young T-Rex grew rapidly, similar to mammals and birds, suggesting a high metabolism. Growth curves indicate that, like mammals and birds, growth mainly occurred during youth rather than continuing throughout life, as in most reptiles. Oxygen isotope analysis in fossil bones can reveal the temperature at which bones formed. In one specimen, isotope ratios from different body parts suggested a temperature difference of only about 4 to 5 degrees Celsius, or 7 to 9 degrees Fahrenheit, between the torso and the lower leg. Paleontologists Rhys Barrick and William Showers interpreted this as evidence that T-Rex maintained a constant internal temperature, with a metabolism somewhere between cold-blooded reptiles and warm-blooded mammals. Some scientists caution that fossilization can alter isotope ratios, but Barrick and Showers found similar results in Giganotosaurus from a different continent tens of millions of years earlier. Studies of other dinosaurs, including ornithischians, show similar evidence of homeothermy, while lizards from the same formations did not. In 2022, Wieman and colleagues used a method analysing chemical byproducts related to metabolism and found that T. rex, along with other dinosaurs, likely had warm-blooded metabolisms comparable to modern birds and higher than most mammals. They suggested that this metabolic trait may have been common to all dinosaurs. Even if T-Rex maintained a stable internal temperature, this does not automatically mean it was warm-blooded. Such thermoregulation could also result from gigantothermy, as seen in some modern sea turtles. Like crocodiles today, openings in the skull of T-Rex may also have helped regulate body temperature. The saber-toothed tiger, often called Smilodon, is one of the most famous and fascinating prehistoric predators to ever walk the earth. Despite its nickname, it is not closely related to modern tigers or lions, but it is a type of big cat that lived during the Pleistocene epoch, a time that stretched from about 2 million to 10,000 years ago. These creatures have captured human imagination for centuries because of their long, curved canine teeth, powerful bodies, and mysterious lives. They are often imagined as ferocious hunters, silently stalking their prey in the forests and grasslands of the Americas, ready to strike with incredible force. The most striking feature of the saber-toothed tiger was, of course, its long, saber-like canine teeth. In some species, like Smilodon fatalis, these teeth could reach up to 7 inches long, protruding far beyond the jaws. These sharp teeth were not designed for biting and holding prey like modern big cats, but rather for slashing and stabbing. Scientists believe the saber-toothed tiger used them to deliver deep, precise bites to the throats or necks of large animals, cutting through flesh and major blood vessels quickly. This specialization meant that while the saber-toothed tiger could take down enormous prey, It had to be careful not to damage its own teeth, as broken canines could make hunting almost impossible. Smilodon had a muscular, stocky body built for strength rather than speed. Unlike modern cheetahs, which rely on incredible bursts of speed to catch prey, the saber-toothed tiger was more like a powerlifter of the prehistoric world. Its short, powerful legs allowed it to ambush prey from close range, rather than chasing it over long distances. Its forelimbs were particularly strong, with massive muscles and sharp claws designed to grip, hold, and pin struggling animals while its deadly teeth finished the job. Imagine a lion holding down a bison, but with even more raw strength packed into a slightly smaller, more compact body. The saber-toothed tiger was not a solitary predator like some modern cats. Fossil evidence suggests that Smilodon may have lived and hunted in social groups much like modern lions. Scientists have found injuries on Smilodon fossils that had healed over long periods, indicating that these animals survived serious wounds. This survival suggests that other members of the group may have helped injured companions by sharing food or protecting them from danger. Such behavior paints a picture of a complex social life, where hunting and survival were cooperative efforts, rather than lone struggles. Smilodon's hunting habits were closely tied to the megafauna of its time. During the Pleistocene, North and South America were home to enormous animals like mammoths, mastodons, giant ground sloths, and prehistoric bison. The saber-toothed tiger likely targeted young, sick, or weaker members of these herds, using its strength and ambush tactics to bring them down. Its powerful jaws and teeth allowed it to kill quickly, while its stocky body helped it wrestle these huge animals to the ground. In essence, the saber-toothed tiger was a specialist predator, perfectly adapted to hunting some of the largest land mammals of its era. Despite its fearsome appearance, the saber-toothed tiger had limitations. Its long canines, while deadly, were relatively fragile compared to the teeth of modern lions or tigers. This meant that Smilodon had to be careful in how it attacked prey, avoiding bones that could break or chip its teeth. Scientists believe that Smilodon used its forelimbs to immobilize prey first, ensuring a controlled kill rather than a frantic struggle. Its hunting style was strategic and precise, relying on stealth, timing, and raw power. The fossil record of Smilodon is rich, especially in areas like the La Brea tar pits in Los Angeles, California. These tar pits are natural traps that captured countless animals over tens of thousands of years. Saber-toothed tigers became trapped while pursuing prey into these sticky pools, leaving behind an extraordinary number of well-preserved skeletons. From these fossils, scientists have learned about the size, strength, injuries, and even the diseases that affected these animals. For instance, some fossils show evidence of arthritis or healed fractures, giving us a glimpse into the challenges these predators faced in the wild. In terms of size, the saber-toothed tiger was smaller than the largest modern lions or tigers in length, but far more robust and muscular. Adult Smilodon could weigh between 300 and 400 pounds, with males typically larger than females. Its body was short and stocky, standing around 4 feet tall at the shoulder, but incredibly powerful for its size. The combination of strength, muscular forelimbs, and long canines made it one of the most formidable predators of its time, able to take down prey many times its size. Saber-toothed tigers also had keen senses, though slightly different from modern cats. Their eyes were forward-facing, providing excellent depth perception for judging distances during an ambush. Their sense of smell was likely strong, helping them detect prey or carcasses over long distances. However, unlike modern big cats, Smilodon's hunting relied less on speed and more on ambush and surprise, suggesting a highly calculated hunting strategy rather than a long chase. The extinction of the saber-toothed tiger, like many other large Pleistocene animals, occurred around 10,000 years ago, likely due to a combination of climate change, habitat loss, and human activity. As the Ice Age ended, forests and grasslands shifted, and the enormous prey animals that Smilodon depended on began to disappear. Early humans, who were skilled hunters, may have competed with these predators for the same prey, or even hunted Smilodon itself. Without enough large herbivores to feed on, the specialized saber-toothed tiger could not survive, leading to its extinction. Its disappearance marked the end of one of the most iconic predators in Earth's history. Culturally, the saber-toothed tiger has fascinated humans for thousands of years. Its impressive fossils inspired myths, stories, and artistic depictions in many early societies. From cave paintings in Europe to sculptures in the Americas, The image of a powerful, toothy predator has captured human imagination for centuries. Today, Smilodon remains a symbol of prehistoric power, survival, and adaptation, frequently appearing in books, documentaries, and even movies about the Ice Age. Studying Smilodon also teaches us about evolution and specialization. Its long canines, muscular build, and hunting strategies show how predators can evolve extremely specific adaptations to survive in their environments. However, these specializations also reveal vulnerabilities. When the world changed and large prey disappeared, Smilodon's very adaptations that made it successful became a limitation. In this way, the saber-tooth tiger is not just a symbol of raw strength, but also a lesson in the delicate balance of ecosystems and the consequences of rapid environmental change. In addition to Smilodon fatalis, there were other species of saber-toothed cats, each with slight differences in size, tooth length, and geographic range. For example, Smilodon populator, which lived in South America, was even larger than its North American relatives, weighing up to 700 pounds in adulthood. This species hunted some of the continent's largest herbivores and showcased how the genus Smilodon adapted to different environments across the Americas. Paleontologists continue to study Smilodon fossils to understand its growth patterns, behavior, and social structures. By examining teeth, bones, and wear patterns, they can infer the age at which individuals hunted independently, how long they lived, and how injuries affected their survival. Modern technology, such as CT scanning and biomechanical modeling, allows scientists to simulate bites and movements, providing new insights into how these incredible predators lived, fought, and thrived during the Ice Age. Another fascinating aspect of Smilodon is its reproductive and nurturing behavior. Fossil evidence suggests that young saber-toothed tigers grew slowly compared to modern big cats, requiring care and protection from adults. This slower growth rate, combined with cooperative hunting, reinforces the idea that Smilodon may have had complex social bonds. Mothers likely stayed with their cubs for extended periods, teaching them how to hunt and survive in a dangerous world full of other predators and harsh environments. The legacy of the saber-toothed tiger extends beyond science and into education and entertainment. Museums around the world, like the La Brea Tar Pits Museum in Los Angeles and the American Museum of Natural History in New York, display life-sized models and skeletons, helping visitors imagine these powerful creatures in their prime. Films, cartoons, and documentaries have dramatized their hunts, interactions with humans, and struggles for survival, keeping the public fascinated with the idea of this prehistoric cat. The giant sloth, a remarkable creature from the past, stands out as one of the most fascinating animals that ever walked the earth. When people think of sloths today, they usually imagine a small, slow-moving animal hanging lazily from a tree in the tropical forests of Central and South America. Modern sloths, however, are tiny shadows of what their ancient relatives once were. Millions of years ago, some sloth species grew to colossal sizes, reaching heights and weights that are hard for us to imagine today. These ancient giants, often referred to as ground sloths, were not the tiny tree-dwelling animals we see now. Instead, they were massive terrestrial mammals, some as large as elephants, roaming the landscapes of the Americas during the Pleistocene epoch, which lasted from about 2 million to 11,000 years ago. The size of giant sloths was truly astonishing. One of the most famous species, Megatherium americanum, could grow up to 6 meters long, or nearly 20 feet, and weigh as much as 4 tons. To put that into perspective, an average modern African elephant weighs about 6 tons, so some giant sloths were not far off from elephant size. Despite their enormous weight, these creatures were built in a way that allowed them to move and interact with their environment effectively. Their legs were sturdy and column-like, designed to support their massive bodies, while their claws were incredibly long and curved, perfect for grasping branches, stripping leaves, and digging. Unlike modern sloths, which are almost entirely arboreal, giant sloths spent most of their lives on the ground, although some species could rear up on their hind legs to reach high branches. The anatomy of giant sloths is one of the most fascinating aspects of these creatures. Their skulls were long and narrow, with powerful jaws capable of grinding tough vegetation. Their teeth were unique, with no enamel but with specialized ridges that helped them chew fibrous plants. Their limbs, especially the forelimbs, were incredibly strong, ending in massive claws that could grow up to 40 centimeters long. These claws were not only useful for feeding, but also likely served as defensive weapons against predators. The skeleton of a giant sloth reveals that they had a robust and heavily muscled build, giving them both strength and endurance, which were essential for survival in a world filled with formidable predators like saber-toothed cats and short-faced bears. Giant sloths were herbivores, and their diet was diverse. They primarily fed on leaves, twigs, fruits, and possibly bark. Fossil evidence suggests that some species preferred certain types of vegetation depending on their habitat. For example, Megatherium lived in open grasslands and forests in South America, where it could reach tall trees and feed on a variety of plants. Other giant sloths, like Erematherium, lived further north in North America and were more adapted to mixed environments, including woodlands and scrublands. Interestingly, their size allowed them to access food sources that smaller herbivores could not reach, giving them a unique ecological niche. Their feeding behavior, combined with their slow metabolism, was well suited to the Pleistocene environment, which could range from warm, lush forests to cooler, drier grasslands. The lifestyle of giant sloths was slow but deliberate. Unlike the quick and agile predators of their time, giant sloths moved at a relaxed pace. Their large size meant they had few natural predators once they reached adulthood. Young sloths, however, were more vulnerable and likely fell prey to large carnivores. Fossilized footprints and trackways suggest that giant sloths walked on the soles of their feet, sometimes leaving deep impressions that indicate their enormous weight. Scientists have also discovered evidence that they could stand on their hind legs to reach high branches, sometimes balancing on their massive tails. This unusual posture, combined with their claws, gave them an almost tree-like ability to interact with the vegetation around them, stretching and pulling down branches to feed. The giant sloths were not only massive and powerful, but also incredibly diverse. The Megatheridae family, which included the largest species, contained several genera and species spread across South and North America. Another well-known group is the Mylodontidae, which included slightly smaller ground sloths like Mylodon. Some species of Mylodon were about the size of a modern cow, still much larger than modern sloths, and were adapted to more open habitats. Then there were the smaller yet still impressive Scelidotheriidae, which occupied niches in forests and grasslands, bridging the gap between enormous giants and the tiny tree sloths we know today. This diversity highlights the evolutionary success of sloths, which managed to adapt to a wide range of environments across 2 continents for millions of years. Fossils of giant sloths have provided fascinating insights into their behavior, anatomy, and environment. Bones, teeth, and even footprints have been discovered in various parts of the Americas, including Argentina, Brazil, the United States, and Mexico. In some cases, remarkably preserved remains have been found in caves or in peat bogs, offering clues about their soft tissues, skin, and even fur. In southern Chile, scientists discovered frozen remains of a giant ground sloth, with skin, hair, and muscles still intact, frozen for thousands of years. These discoveries are incredibly rare and invaluable, allowing paleontologists to study the creatures in detail and understand how they lived and moved. The extinction of giant sloths is a topic that has fascinated scientists and the public alike. These enormous creatures disappeared roughly 11,000 years ago, at the end of the Pleistocene epoch, during a period known as the Quaternary Extinction event. This event saw the disappearance of many large mammals across the Americas, including mammoths, mastodons, saber-toothed cats, and giant bears. The causes of this mass extinction are still debated. Climate change likely played a role, as the last ice age ended and the environment transformed, affecting the availability of food and altering habitats. Additionally, human hunting is considered a major factor. Early humans in the Americas were skilled hunters, and their arrival coincided with the decline of many large mammals. Archaeological evidence shows that humans hunted giant sloths, leaving behind butchered bones and tool marks. The combination of environmental change and human impact created a situation that the slow, reproducing massive sloths could not survive. One of the most famous discoveries related to giant sloths is the Megatherium americanum. First described scientifically in the 18th century, Megatherium quickly captured the imagination of people around the world. Its enormous size and strange appearance made it a symbol of prehistoric life. Skeletons displayed in museums today allow us to see the full scale of these giants, with their long, clawed forelimbs and heavy muscular bodies. Some reconstructions suggest that Megatherium could stand upright like a two-legged creature, stretching its massive arms to pull down branches for food. This image is both awe-inspiring and slightly terrifying, as it reminds us of the sheer scale of life that once existed on Earth. The Mylodon, another famous giant sloth, provides a slightly different perspective. Smaller than Megatherium but still formidable, Mylodon was more adapted to forests and open grasslands. Remarkably, some fossils of Mylodon include preserved skin and hair, giving scientists clues about their appearance. Evidence also suggests that Mylodon might have dug burrows or shelters in which it could rest or hide from predators. Unlike the massive open-land Megatherium, Mylodon seems to have had a more flexible and adaptable lifestyle, making it a fascinating subject for study. In addition to their physical traits, giant sloths may have had interesting social behaviours, though much of this is speculative. Some scientists suggest that they were mostly solitary animals, like modern sloths, while others propose that they could have gathered in small groups, especially in areas with abundant food. Their slow movement, combined with their size, would have made them less vulnerable to predation, allowing them to focus on feeding and reproduction rather than constant defense. Fossil evidence does not provide clear answers about their social lives, but it does show that these creatures were well adapted to survive in a variety of environments, from open plains to forests, over thousands of years. The legacy of giant sloths continues to influence our understanding of evolution and ecology. By studying these creatures, scientists gain insights into how large mammals adapt to different climates and habitats, how they interact with vegetation, and how ecosystems functioned in the past. Giant sloths also provide a window into the effects of climate change and human activity on large animals. The Pleistocene extinctions remind us that even massive, seemingly invulnerable creatures can vanish if their environment changes too quickly or if humans intervene. This lesson resonates today, as many large mammals around the world face similar threats from habitat loss, hunting, and climate change. Interestingly, giant sloths have also captured the imagination of people in popular culture. They appear in documentaries, books, and films about prehistoric life, often depicted as slow-moving giants with impressive claws. Their unique combination of size, strength, and apparent gentleness makes them both fascinating and endearing. Some indigenous cultures in South America have oral traditions and myths that may have been inspired by the bones of giant sloths, interpreted as enormous creatures that once roamed the land. These stories highlight the lasting impact that these animals had on human imagination, long after their extinction. The study of giant sloths is still ongoing. New fossil discoveries continue to refine our understanding of their diversity, behaviour, and evolution. Advances in technology, such as CT scans and DNA analysis, allow scientists to examine bones in unprecedented detail and even attempt to extract genetic information from well-preserved specimens. Such studies could reveal relationships between different sloth species, their diets, and their movements across ancient landscapes. Additionally, examining the microstructure of bones can provide insights into growth rates, age, and health, revealing a more complete picture of these amazing creatures' lives. The term raptor immediately conjures images of fierce, swift, and intelligent predators, creatures that have captivated human imagination for centuries. In the modern world, the word raptor often refers to birds of prey, such as eagles, hawks, falcons, and owls, but the roots of the term also trace back to ancient dinosaurs, specifically the dromaeosaurids, which are often popularly called raptors, thanks in large part to movies and popular culture. In this exploration, we will examine raptors from both perspectives: the prehistoric dinosaurs that once stalked the Earth, and the living birds of prey that continue to dominate the skies today. Raptors, in their prehistoric sense, belong to a fascinating and diverse group of theropod dinosaurs, known scientifically as dromaeosaurids. These creatures roamed the Earth during the late Jurassic and Cretaceous periods, roughly from 165 million to 66 million years ago. They were generally small to medium-sized carnivores, though some, like Utahraptor, could reach formidable lengths exceeding 6 meters. Dromaeosaurids were characterized by several distinctive features that set them apart from other dinosaurs. Perhaps the most famous is the enlarged, sickle-shaped claw on each foot, which could grow up to 30 centimeters in some species. This claw was likely a formidable weapon, used to slash at prey or grasp and hold struggling animals. Coupled with strong, flexible legs, these claws made raptors efficient hunters capable of tackling prey larger than themselves. Another defining feature of these prehistoric raptors was their long, stiffened tails, which acted as dynamic stabilizers. This tail structure allowed for incredible agility and balance while running, leaping, or maneuvering through complex environments such as dense forests. Many raptors also had elongated arms ending in three-fingered hands, with sharp claws capable of grasping and manipulating objects. In some species, fossil evidence shows quill knobs on their forearms, suggesting the presence of feathers. This feathering may have served multiple purposes, including thermoregulation, display, and potentially aiding in balance and maneuverability while running or hunting. In essence, these dinosaurs were an evolutionary combination of speed, agility, and intelligence, which made them successful predators in their ecosystems. Intelligence is another attribute often associated with raptors, especially in popular culture. Paleontologists have long speculated about the cognitive abilities of dromaeosaurids due to their relatively large brain sizes compared to body mass, particularly in the forebrain regions associated with sensory perception and motor control. Fossil evidence suggests that some raptors may have hunted in coordinated packs, a behaviour that would have required communication, strategy, and social organisation. However, while the idea of cooperative pack hunting is compelling and widely depicted in media, it remains a subject of debate among scientists. Nevertheless, there is little doubt that these dinosaurs were highly adept hunters, capable of complex behaviours that gave them an edge in their environments. The popular imagination of raptors owes much to depictions in films such as Jurassic Park, where Velociraptor was portrayed as a cunning pack-hunting predator. While these portrayals often exaggerate aspects of size and intelligence, they have cemented the raptor's image as a symbol of predatory cunning and ferocity. In reality, Velociraptor was considerably smaller than its cinematic counterpart, roughly the size of a large turkey, with a weight of around 15 to 20 kilograms. Other raptors, like Deinosuchus and Utahraptor, were larger and more powerful, but none quite matched the dramatic scale of their Hollywood renditions. Despite these exaggerations, such portrayals have sparked widespread interest in paleontology and have inspired generations to learn more about these fascinating creatures. Moving from the prehistoric to the present, the term raptor has also come to define birds of prey, a diverse and ecologically crucial group of avian predators. These modern raptors include eagles, hawks, falcons, kites, ospreys, and owls, all united by their predatory lifestyles, sharp talons, hooked beaks, and keen eyesight. Raptors occupy the top tiers of many ecosystems, acting as apex or mesopredators that control populations of smaller animals, maintain balance within food webs, and influence the behaviours of other species. Their presence in an environment often serves as an indicator of ecological health, highlighting the importance of their conservation. One of the most striking features of modern raptors is their extraordinary vision. Eagles, for instance, have eyesight that is estimated to be 4 to 5 times sharper than that of humans. Their eyes are equipped with large retinas, a high density of photoreceptor cells, and a deep fovea that allows for precise long-distance vision. This visual acuity enables them to spot prey from hundreds of meters away while soaring high above the landscape. Hawks and falcons share similar adaptations, which make them formidable hunters capable of detecting and tracking even the smallest movements on the ground. Raptors are also known for their powerful talons and beaks, specialized tools for hunting and consuming prey. The talons, curved and razor-sharp, are used to seize, immobilize, and kill animals, ranging from insects and rodents to fish and other birds. The hooked beak is designed for tearing flesh, efficiently processing food in a way that sustains the predator. Some raptors, like owls, have evolved silent flight through specialized feathers that reduce noise, allowing them to approach prey undetected. Falcons, on the other hand, are renowned for their speed, with the peregrine falcon capable of reaching over 300 km per hour during its hunting stoop, making it the fastest animal on the planet. The behaviors of raptors are as diverse as their forms. Many species are solitary hunters, relying on stealth, ambush, and aerial agility to capture prey. Others exhibit complex social behaviors, such as cooperative hunting or long-term pair bonds. Eagles, for instance, often mate for life and engage in elaborate courtship displays, including aerial acrobatics and synchronized flight patterns. Nesting is also a critical aspect of raptor life, with many species building large, durable nests called eyries in elevated locations such as cliffs or tall trees. These nests can be reused and expanded over many years, sometimes reaching extraordinary sizes. The commitment to parenting among raptors is remarkable, with both males and females often involved in feeding and protecting their young until they are ready to fledge and survive independently. Ecologically, raptors play a vital role in controlling populations of prey species, such as rodents, small mammals, insects, and fish. This predatory pressure helps prevent overpopulation, reduces the spread of disease, and maintains a balance within ecosystems. Raptors also influence the behaviors and distribution of other animals, creating what ecologists call landscapes of fear, where prey species adjust their activities and habitats in response to predation risk. Such indirect effects highlight the intricate interconnectedness of ecosystems and the importance of top predators in maintaining biodiversity. Raptors have also held profound cultural significance across human history. In many ancient civilizations, they were revered as symbols of strength, vision, and freedom. The eagle, for instance, has been a potent emblem of power, courage, and nobility in cultures ranging from the Roman Empire to Native American societies. In Egyptian mythology, the falcon-headed god Horus represented the sky, kingship, and protection. Even in contemporary symbolism, raptors remain icons of vigilance and authority, appearing on flags, coats of arms, and national emblems. Beyond symbolism, humans have also engaged with raptors through falconry, a practice dating back over 4,000 years. Falconry involves training birds of prey to hunt in cooperation with humans, a skill that requires deep knowledge of raptor behavior, patience, and respect for the animal's instincts. Despite their formidable adaptations, both prehistoric and modern raptors face significant challenges. Fossil evidence suggests that many dinosaur raptors were impacted by environmental changes, competition, and the catastrophic events that ended the Cretaceous period, leading to their extinction around 66 million years ago. Modern raptors also confront numerous threats, particularly from habitat loss, pollution, and human persecution. Pesticides such as DDT historically caused dramatic declines in many raptor populations, notably the bald eagle, by thinning eggshells and reducing reproductive success. Conservation efforts, including habitat protection, legal safeguards, and captive breeding programs, have helped some species recover, but ongoing vigilance remains essential to ensure their survival in a rapidly changing world. Raptors also serve as important subjects for scientific research. Ornithologists and paleontologists alike study these animals to understand evolutionary relationships, biomechanics, sensory systems, and ecological interactions. Modern technologies, such as satellite tracking, high-speed cameras, and genetic analysis, have expanded our understanding of raptor movements, hunting strategies, and population dynamics. Similarly, fossil studies using advanced imaging techniques, such as CT scans and three-dimensional modeling, provide insights into the anatomy, behavior, and evolution of dinosaur raptors, revealing connections between ancient species and modern birds of prey. The evolutionary link between prehistoric raptors and modern birds is one of the most fascinating stories in natural history. Fossil evidence indicates that birds are direct descendants of theropod dinosaurs, and features such as feathers, hollow bones, and certain respiratory adaptations first evolved in dinosaurian ancestors. Raptors, with their agile bodies, feathered forearms, and predatory behaviors, exemplify this transition.